Welcome to everybody. My name is Roberto Galeazzi, and I'm the head of this new DTU Center for Collaborative Autonomous Systems. It's a great pleasure for me today to be here with you and to have the opportunity to launch publicly the center and to set the scene for a long-term collaboration with each and every of you that have the wish to impact society in the future years through development and actualization of collaborative autonomous systems in the different domains that these type of technologies could benefit. Before we set going with the nice and I would say diverse program that we have arranged for you today, which was driven by the wish to actually show that autonomous systems is much more than what people maybe normally think. It's not only about robotics, it's much more than that. Autonomous systems will impact many other technological domains, from transportation to health. And I think that the program was shaped in a way to convey this message, that many domains are at stake and many technologies could actually benefit. But before we venture into that, I must in these times, let's see if we can manage. It is necessary to make sure that we are all clear about the rules of the game. So this is a standard safety briefing that I must read for you, since we are in challenging times. So as of course you can see and experience, we have DTU has reopened and we would like to keep it so. So it's extremely important that we all act in a wise and concerned way in order to limit the risk of infection. We as a public institution adhere and follow closely the authorities' recommendation, and of course, as you are well aware, the main rules concern distance requirements, sanitation of hands, and that, of course, if you don't feel well, despite we will love to see you here, maybe you should reconsider your attendance. And obviously, this is because we want to protect each other and not compromise the reopening of society. If any of us, and of course it can happen, starting from myself, I get too close to you because maybe we haven't seen in a long time and I'm excited about the day, or you see that I touch things and forget to sanitize my hands, please tell it up my face. Certainly I will receive it with a smile and I will not have a doubt about, so to say, washing my hands once more. We all got used to this nowadays. During the event, as you have seen, there will be several breaks for refreshments and also for networking. During the coffee breaks, this of course, what is written here was my misconception. The rules will be that we have arranged the deliveries of beverages and food on two lines, one right behind the poster panels and one on the counter at the end of the room. Please, around 10, quarter past 10, there will be the coffee break. So please then divide in two rows and sanitize your hands before accessing the food, and then of course take what you need. The lunch is already wrapped for you, so also in this case it's very simple. There will be a bag with a sandwich and some water that you can take while we will move towards the autonomous system test arena. Those of you that have requested special or have put forward special dietary needs, they will have to contact my colleague Susanne over there, which will be able to help you out with whatever you are requested. Okay, so now we are ready to roll, and it's with great pleasure that I introduce our DTU president, Hannes Bjerklau, that has taken time out of his very busy schedule to join us in here today, and spend a few words to introduce the launch of the new center. Thank you very much.
Thank you very much, Roberto. I hope you can hear me, everybody. And I'd like to, of course, start to wish you all a very good morning and a warm welcome to the grand opening of CCAS. As I just learned, we're going to call the new baby. As we say, of course, all good things come to those who wait. And we have all now waited for this opening for quite some time, but it's finally here, and I'm sure, I trust it will be a great day, and I'm certainly sure it's a great program that my colleagues have put together with a very packed and interesting day. Naturally, as we already heard, much focus has been on the pandemic, but fortunately, I would say the sustainability agenda is slowly regaining momentum, and I think we can very much welcome this development for many reasons. And I believe that we have to point out that sustainability is not just about something green, it's about also autonomous systems to a very high degree, actually. Although some people might find that this a little harder to understand, or at least initially. But I think autonomous systems, they come in, as we already heard from Roberto this morning, they come in many different types and forms, and they have the potential to radically transform our society. They can do that by improving our public transport, they can reshape the logistics sector, they can strengthen assisted living, they can enhance the healthcare system, enabling small cities to work efficiently, safeguard human lives in cases where we have dull, dirty or dangerous jobs, and of course extending the workforce lifetime instead of sending them on an early retirement. I think that would be good for many reasons. So in many ways you can say, as they also say, what's not to like? The future of autonomous systems hold, I believe, a great promise, as has already been documented in a recent report from ATV. In Denmark, as a whole, is doing well on this agenda, but I also think we can do much more, and we should do much more in order to make the promise of autonomous system a reality. And we should do that because it would benefit all of us. And this is why I'm certainly happy to be here, at least virtually today, for this grand opening in Center for Collaborative Autonomous Systems, and also, of course, as you will see later, the Autonomous Systems Test Arena. Indeed, at DTU we aspire to become a leading international research and innovation hub on autonomous systems, and this center and the test arena, we believe, will be central to this endeavor, along, of course, with our Master of Science education in autonomous systems. That will happen through inter- and transdisciplinary research and innovation and education, as well as world-class research infrastructure. We will explore processes, methods, technologies, and experiment, verify and validate technologies for the actualization of autonomous systems in future society, for a brave new world and a good sustainable one too, I believe. And of course, educate the engineers who will make this happen for the next many years to come. And we're looking forward to doing this together with you, in collaboration, of course. Together, I think we can take autonomous systems and the digitalization of society to a whole new level. But, and I assure you this will be my last words here today, before I let you get on with the great program here, I like to underline that we always do this for the benefit of society, or as we say in DTU these days, we make technology for people. So congratulations on the new center, and I certainly wish you all a great day. Thank you very much.
Thank you very much, Anas, for really taking the time to be with us today. And yes, everybody, I guess, looks forward to this new initiative. And we are pleased that DTU is with his full force behind the launch of the center. Thank you very much. So now we can start the technical program, and I can see that Professor Asgeir Sørensen is already with us. So let me... Yes, Asgeir, can you hear us?
Yes, I can.
Okay, that's great.
Can you hear me?
Yes. So now we will have to coordinate. So we have a few minutes to coordinate the presentation, since I have your slides. Just a moment. So now no. Yes. Yes, so let's start the day. Our first speaker is Professor Asgeir Sørensen from the Norwegian University of Science and Technology. Asgeir is head of Center for Autonomous Marine Operation and Systems at NTNU, and has been so for by now quite a few years. Before that, he was already heading the former Center of Excellence for Ships and Ocean Structures, which was also focusing very much on the development of autonomous systems for marine operations. It's a great pleasure to have Asgeir here today because of his renowned leadership in the sector, his ability to conjugate research and innovation at the university, as well as entrepreneurship in the private sector. And we are indeed extremely pleased that Asgeir has accepted to be a part of the advisory board of the Center for Collaborative Autonomous Systems, covering the area of research and innovation. And we look forward to a long-standing a long collaboration with him, and to also learn from the successes that he has already seen through his experiences at NTNU. So it's a great pleasure once again to have you here, Asgeir, and I will do my best to coordinate with you the talk. So I will be here switching the slides. Please, the stage is yours.
Thank you so much, Roberto, and dear friends in DTU, colleagues, but I will mainly say friends, because we have had very, very long relationships. I have had that personal, but also I have seen my colleagues is doing the same. In particular, I have had the pleasure to work very closely with Roberto Mogens for I don't know how many decades, Ulrik, and many, many others. So Good to hear from you, all of you. I am actually currently on a research campaign here in the outside of Trøndelag. So I'm sitting in a research space. So in a way, COVID has learned us about we can actually still participate in events like this, and so that is something good about all this. But again, first of all, congratulations with the CCAS. I am extremely happy to be involved, and so we can start. And my background is more on the blue economy. So Roberto, you can start to click. Yeah, so the intention was to go a little bit about reminder what is really the blue economy from our perspective, and then summing up why autonomy in this field and what is the difference between automation and autonomy, testing, verification, and some examples of what we are doing. That is the talk for today. Next, please. I think when we are doing an investment, and Rector did point this out very well, you have your vision for what you are contributing to the society. We do the same. We have knowledge for a better world. It's actually the vision for NTNU, and it is indeed giving me inspiration. So we are using, as you will see, tremendous resources in this field in Norway, and we have to have a holistic view. And even if some of these terms, in a way, may be overused and in some misused, we still have to keep our eyes on the holistic view about global challenges, value creations. We have to have proper management, and then the role of the universities is actually to create knowledge. So next, please. There is no doubt that global challenges such as global warming, greenhouse gases, are serious. But we also, at least what I have learned, is also the important to take care about the ecosystems and biodiversity. Maybe that is an looked and under-addressed problem in all these efforts to look for global warming. But these are connected. Next, please. We have to, both DTU and NTNU, we have a huge responsibility to help the society also to create businesses that for in the blue area is the marine related. But we also have, of course, all other industries, as you are going now to address in this new center. Please, next. And you can take all just to see the FN. Yeah, but what we also see is that there are dilemmas all the way. It is so the success is very much that the politicians, the rule makers, those making standards are well connected to this holistic view. And for us, I think we should never compromise the importance of bringing knowledge into this. We call this knowledge-based management. And this has to be aligned with the UN Sustainable Development Goals. And from my perspective, these goals is actually the biggest market study ever done. And we see also how different businesses are now making this not to restrictions, but rather to an opportunity for creating new businesses. Next, please. Here, what we have, at least in Norway, you also have that in Denmark, is if you look into the blue economy, we call this a supercluster. You have shipping, you have oil and gas, you have fisheries, we have aquaculture, we have tourists, we have a huge coastal infrastructure. We see also how now offshore renewable energy is coming as an important part. But if you are going further into the oceans, we have hardly seen only fractions of the oceans and the potential of oceans for new food, but it is also new medicines, and we have to look into I would say the health of the oceans, because also we see the oceans are extremely important for the whole climate and life on Earth. So how we should also manage this is crucial. Next, please. Okay, so now a little bit more on the theoretical background from our side. Please, next. you could say the reason for why we go into this and what are we really facing, at least for those of us that has been in this field for a while, we are I would say, in the middle of a digital big bang. Just take next. And this is enabling technologies, which is really creating huge change in daily life and also for universities and for businesses. And I see this is one of the really big enablers why we are speaking about what we do today. There is also coming up other enabling technologies we should keep a very strong eye on, which will be connected to this one. For instance, material technology, biotechnology. So how we, on the university viewpoint, we should, in a way, be the first one to first do research here, but also to start to do integration in an interdisciplinary setting. Next, please. So driving businesses for autonomy, you could say that they are within aerospace, robotics, marine robotics, automotive. Next, please. And you could say one reason for why these areas have been driver, one thing is, if you look into aerospace and marine robotics, is that you have lack of communication. These units simply have to deal or survive on their own. And that has been one reason for making them, I would say, a higher level of intelligence going into autonomy. If you go on advanced ships, oil and gas ships, cruise ships, we have been working with autonomous functions for decades already. I spent 10 years of my professional career in ABB. And if you're looking to all safety systems on such units you see there, and if you're looking to a lot of advanced power management systems, to drilling control system and how you interconnect them to the dynamic positioning system, autonomy is really not new at all. We have actually taken benefit of autonomy typically in cases where we don't have time to think and to interact with the operator. The system has to be dealing with this on their own. Next, please. So that has actually also led to autonomous ships. And what actually was an eye-opener for me, because if you're looking to automation, one reason for automating processes is actually that you are doing things faster. You can reduce what we call the operational expenditures, that is OPEX. But what is also a big difference here is also related to CAPEX. If you're looking to autonomous ships, if I could make these ships without having all this additional, you could say, infrastructure to keep people on board, I could actually also build them cheaper. So that is also a game changer coming in, that you should not only look into OPEX, but also to CAPEX. And what we see is that autonomy is also creating completely new innovation within business models. Because if think you are a ship operator, if you, in a way, are looking to the future, I'm not speaking not on all ship routes, but some segments, you see a trend where the system vendors, the big system vendors, together with the owners, or you could say the client of the operations, they are now starting to connect without any ship operator there. So that is examples we have with Yara Birkeland, where Yara, together with Kongsberg, enter into a new segment, a new business. We see the same with ASCO Maritime, where actually the ASCO, they are called the Norwegian group for consumer markets, are going together again with system vendors. So this is also, you could say, a big business transformation that is taking part. You will see new players are coming up for this, and this is also interesting. But still, of course, the shipping companies has to keep pace on this, but they have to be awake, else they will be out of business. But what is also interesting in terms of this picture here, if you look into maritime, one of the biggest challenges in according with, or for us, is to meet also IMO requirements to reduce emissions with 50% in a global setting. And you will do a lot here regarding machinery systems, optimizing hull, and route planning, etc., etc. But maybe one of the bigger, you could say, enablers also to be successful here is actually that you go autonomous. You could actually just reduce the speed. So we will see new shipping routes is coming up, also in deep sea shipping, that may go with 5, 4, 6 knots. And since you don't have people on board, you don't need to rush that fast. So there is not all goods that needs to be transported with 14 or to 20 knots. So that this is also will be a huge change. If you're also looking into urban and rural transport, we see that we have also to take benefit and use the waterways again to transport people, and they will of course be green. We are speaking about greener ports, so you will see new possibilities coming up. Next, please. So of course there is huge challenges. Are we ready for autonomous ships and ports? Well, I think so. It is easier to go with an autonomous ship if you compare that to an autonomous car, and you have more space. But of course, there are numbers of challenges related to cybersecurity, testing, verification. How do we deal with manned and unmanned ships? And will it be, you could say, hybrids of this, where you go unmanned and partly remotely controlled in a part of the route, and then you shift into manned operations or assisted operation? And I think that will be the case. Next, please. What is also coming up, if you're looking not only to autonomous ships, but now I'm going more into robotics, and this is, I will come even more back on this. And we also see that we are setting up new organizations, we could call them robotic organizations, where we actually are having a network and swarms of robots. They could be one type, or they could even be of different types, operating in different domains. So how should the robot helping robot, and how should the collaboration be done? And this is also a huge possibility regarding scalability, where actually also open sources and connectivity, etc., will be crucial to be successful. And I think here we have tremendous of possibilities, and we, in the marine space, we are already starting this in a quite, I would say, determined manner. And now we can go to the next example, where you could see a robot is helping a robot, where you could also be out of the box and being creative. Please start this video. Is it any noise there, or?
There is no
okay.
no sound coming out from the video.
But I can speak for this video. But what you see here is that use of in this case, an unmanned aerial vehicle for departure from a ship is easy, but in order to and launching, but in order to land, it's a highly risky operations. So in this case, you see how actually you could still be successful by simply putting the landing outside the ship. And for oil and gas operations, this is extremely important, so you don't have any explosions, etc. Okay, so here you see robots are helping robots. Next, please. What we also have been looking into is what I mentioned, the heterogeneous systems. So we are working, if you're going from remote sensing in space to unmanned aerial vehicles, and also to autonomous vehicles, and then underwater, we see also how could we actually optimize, you could say, the control and operation of all these different devices, because they have different capabilities in spatial and temporal domains. And this is could be communication networks, it could be also mapping and monitoring networks for the marine environment, but it can also, of course, also, and will and are used also for land operations. So now we can switch to the next. Hopefully the voice is working. There is no voice.
Unfortunately not.
Okay, just run it. But the idea here is actually where we are seeing that by having space operations, and we see this also as a huge explosion in connectivity for communication, but we also see a democratization of the space where small sats in particular is now becoming robust enough, cheap enough, that you actually could make your own satellite, and here you could customize payloads, and they can be typically in operations for 4 or 5 years, and giving new possibilities for sensing and communication where you before will have to be there by ships or other systems. In this example, we are looking into hyperspectral imaging. These satellites are going to be operating in polar orbits, where they actually also will be looking into upwelling areas and also of algas in order to help and monitor the operations. And of course, there will time to time be clouds there, and they are not able to see below. But so that is a part of that. But if you also are cooperating internationally, they could also be used for that purpose. So here you see where you actually are using remote sensing, and this is hyperspectral imaging, where we by colors are able to see, you could say, that you have new layers coming up. And if you are in situ there, you are not actually seeing this shift in water quality masses. So here you see very good examples where you actually have to zoom out and then zoom in. And I think a lot of the success in the collaborating robots is actually where you see they are actually collaborating to have this view. So now you could actually go down and be in situ with you could operate with drones, but you could also start to control unmanned surface vehicles to do that. We can just continue. So if you summarize it here, so you can just click all the way. You see the end. So the drivers we have here, it is obviously what we call dull, dirty, dangerous operations. But we also see that these devices are cheaper, and they are unique, and you can actually do solutions which you actually could not. Also, as Rector mentioned in his talk, you could also enable new functions, new markets, but one of the big success criteria here is actually to go for scalability. This means that you should have open systems, they should be able to interact, etc. And we see that you are actually also not only looking to OPEX, but you could also go into CAPEX and having a change on that. Next, please. Yes, so that's why. And now, next, please. Yeah, you can go through. Yeah. So, what is the difference between automation and autonomous system? It is really not a hard borderline here. At least if you're looking to how control has been evolving. If you're looking to the work by Mugens, for instance, on fault-tolerant control, he has been a pioneer in this field, and this is a crucial part of autonomous systems. And finally, I would say, people also in the academia, they have seen it, of course, but finally, the bigger groups are actually now seeing the value of such work to be able to reconfigure, plan, and replan. So if you spoke with Mugens, he could say that I have done this for decades already. But these are essential functions in autonomous systems. But they should also be able to learn, adapt, and if you are speaking with adaptive control, we have been doing that as well. But there is still something new, and that is we are going into a field where you don't have obvious, you could say, decisions. So you are getting into what we call a deliberative world. And here, where also knowledge and how this knowledge is handled becomes a new term. So in a way, we are speaking about the increased intelligence in these systems. Next, please. Yeah, and you can go through all the animations. So there are different levels. These are from defining autonomy. These are defined by US NIST and US DOD. There are also different definitions here where you have 10 levels, you have on shipping 5 levels. But the whole point is that you see there is a different levels where the human, in a way, are less and less involved in the decision making. And we don't go into detail here, but just say that there is not either or. There is a mixture of components of autonomy. Next, please. Yeah, and what I also think is crucial is that people are mixing autonomy with unmanned. Or because an unmanned system, of course there is no operator on board, but an unmanned system could be perfectly well remotely controlled. And many of the ships, actually, you are simply moving the control room from the ship to the land. And with good communication networks, you are controlling the ship more or less as you were on the ship. So of course, but if you lose communication, either it is on the ship itself or in this remotely controlled world, the system has to have capabilities to handle this themselves. So that is also important to be aware of. Not all unmanned systems need to be autonomous. And also manned systems, as I mentioned for oil and gas ships, can have plenty of autonomous functions on board. So this is really not that new. Next, please. There are different elements of autonomy which is crucial, and I mentioned some of them here. There is obvious that one of the most crucial, you could say, areas is actually sensing and situational awareness. And this is related to navigation sensors, and here we see how well the car industry, automotive industry, has in a way been able to scale up with this just to help the driver, but then you also get the cost down, and we could put these sensors also in other applications. Anti-collision systems, but also payload sensors, because if we are, for instance, doing this remote sensing, we are also starting efforts to, in a way, analyze the sensors on the fly. Next, please. There's numbers of these. And in a way, you could say we have what we call reactive control systems, but going further. Take next, please. So the new element is actually that we are building up more knowledge into the control system, as we already have done. Next, please. And you see you actually introducing optimization, learning mechanism, and you are building up the yellow part of the system. Next, please. So I think this is what we, from our viewpoint, has seen about the most critical part, is how do we deal with this perception of information? How do we comprehend this information? And can we project it into future situation and put this into to the systems? That is what this is very much about in research terms. Next, please. So what you see here is actually a control architecture. This could be on a ship, it could be on a robot, where you have different levels of control execution, guide and optimization, but you also have the mission layer. And next, please. And what you see here is the red part on the top. That is where automation comes into play, and where we now cannot work anymore alone as a control engineer. For instance, in marine robotics, I have to team up with the marine biologists in order to start to understand the planning, the replanning. I have to also start to understand the sampling of what they are doing. Next, please. And you can go through this. So, yeah, and next. So the automation or autonomy part is actually about to automate the top level with the lower level. And we have to look into new methods in order to do this in a proper manner. And here I think we have to learn from computer science. So people like me from the control society, we have actually now also much stronger to bridge this into computer science. Next, please. So what you see here is actually a layout from an underwater vehicle. where we have typically on the low level, execution level, are working with the control systems, navigation systems. We have a guidance system and we have some mission control. But if I'm looking to the AUVs we have today, are using now in the bay, they are quite stupid. We are pre-planning the mission, and then they have a payload sensor, and we are hoping that they are taking good sensor data. And then we take up the robot, and then we start digging into the data, and then we maybe become happy or maybe not. So the idea here is actually that the processing of the payload data should be done more on the vehicle itself. So if there is some glitches in the data, it should in a way go back and take that again. And if you are looking for particular, you could say, species, then you could maybe analyze some of this data, and you go back and revisit it with more advanced sensors in order to have the proper picture. And to the right, you see different, you could say, call it methods, toolbox, which we actually have to deal with. And the yellow one is quite interesting. They are about risk and failure handling. And as already mentioned, with Mugens as one of the big pioneers in fault-tolerant control, you see how also this is coming into play, but also how are you actually putting the seafarers' risk assessment skills into a robot. Next, please. So this is actually, I've come more into that now. But one of the challenges we see here, there is legal considerations, there is social acceptance. Okay, we have created new job places, but we are also taking some away regarding employment issues. But there are safety barriers and risk management, security issues. There's a huge lack of standards of how we should do with this. And then the final question, how should we verify them? How should we test these systems properly? Next, please. So, yes, next, please. So here you see an example of classification of risk. And for our research, we have seen this as, together with situational awareness, maybe as the second most important. How should we classify a risk regarding to mission complexity, to the environmental complexity, and the ability to interact from a human point of view? So here you see, and you will obviously see that different applications are scoring differently in this picture. And so when I'm saying it's easier to drive an autonomous ships compared to a car, you could easily justify it by about both the environmental but also the mission complexity. Next, please. Yeah. So if we from if you're from you could say computer control system world, where we normally take a DP system, a dynamic positioning system. Together with Kongsberg, I also launched a company called Marine Cybernetics. We proposed hardware-in-the-loop testing for testing software-based system. And for a DP2 system, which is pretty complex, there are 4,000 single failure modes that may occur in that system. But if you're looking to it from an operational point of view, there are 4,000 factorial failure combinations that may occur. So it's, in practical terms, infinite. And if you now start to take the next level by using artificial intelligence and all these elements, you actually get, in a way, unless you do this properly, you end up in an uncontrolled environment. And so that is why I'm saying that we need to have methods, both formal. Next, please. We need methods, both formal, where we have to develop theory to deal with this complexity, but we also need, you could say, informal testing methods, where we actually are testing the implementation, not only the design, but the implementation. And everybody working with software systems know there are design flaws. So this is also a huge challenge in this era. And where I'm saying now that we have more than before also connect with the software science guys. Next, please. So this is an example where you are using a digital twin in order to, in a way, create, you could call it a virtual test environment where you actually could use computers to test computers. Next, please. What you see here, now I'm going a little bit back to show you some examples. So this is looking to the oceans again, what we see here is processes taking place in the oceans. And there are plenty of those. And if you know, take next. And you can just animate to it. In a way, what you see here is that you are going to have robots dealing with both dynamics and trends and what is happening over decades, but also you should have ability to operate from millimeter accuracy resolution to covering the whole Earth. And here you definitely see how the different platforms are in a way connected to each other. Next, please. So what we also see here is that going from this, call it the robotic world, we also need to complement this also with more advanced models. This could be of the oceans, it could be also of the terrestrial areas, whatever. So the combination of numerical advanced models from natural science together with the robotics is what we also see a huge research era coming ahead of us. Could do similar type of thinking in the medicine. Next, please. So what we actually do now, just go through the animation, is that we are now, these days in Norway and in Trondheim, we are working with setting up a fleet of robots where we actually should be able to call it digital oceans. And together with other partners in Norway and also an international play coming up called RevOcean, we are trying to digitize the whole oceans. But here we need to cooperate in order to see the complete picture from pole to pole. Next, please. So this is the Bay of Trondheim. So what we also have been working heavily with now these days, this because I'm now into the examples here, is we have now installed several of offshore equipment, but also if you go to the next one, we have started also to work with subsea docking, where we also see that by having a template submerged, we are able also to keep the robots underwater for a longer period of time, where they could do charging of batteries, but they could also download data and putting up new missions. Next, please. So here you see where we actually just outside the Bay of Trondheim have been putting the world first, I would say, industrial docking station together with Equinor. So this is going now to be used as a maintenance platform for oil and gas installations. If you then supplement this also with floaters, you actually are creating hubs of these stations that could be used for offshore wind farms, for fish farms, where you're doing inspection both underwater, but also having drones, you could do superstructure infrastructure inspection. And this is also important area where we jointly between Denmark and Norway need to do this together. Next, please. Here you see an example of this docking station with our also newly developed robot called Illume, which is also inspired by biology. Just giving you a picture of that, where we actually see that new novel concepts actually could evolve from this. And now I have another video, but I think we skipped that because you don't have the noise. I will just wrap up to reach this to innovations. And I think with CCAS, I think also because I mentioned it briefly, I have about 50% of my time from industry, both from ABB but also from startups. And then I have the rest of my time from academia. But sometimes you could say we have what we call market-driven innovations. But you should not underestimate the value of what I call researcher-driven innovations. And what I hope is that you are creating, you could say, an environment where actually you have license to create, and where you actually could do what we call the disruptive changes. And where there is not that hard regime regarding IPR, meaning that you are, in a way, you become only incremental. Incremental is still valuable, but the disruptive changes, I expect them to come from university environments and the surroundings about that. So we have tried to do this in AMOS, and if you go to the next. In order to do this, we have to communicate we have to see this picture, both ourselves, but also in relations to our partners. Of course, most of innovations we are giving here is to industry, and it could be governmental agencies, dependent on the field you are. But we should more than before, in a way, also start to have spin-offs where we are in a way creating the new industry. And don't expect the industry to do this. This is the expectation I put on the shoulders of NTNU, I put them on DTU. So you should actually increase the ambitions here to create this, and here we can be inspired by groups in Silicon Valley, also in the Boston area, and we have to be far better in this in Scandinavia and Europe. Next, please. And in order to do this, you have to create a culture for this. You have to have acceptance at universities. You have also to have organizations to do this. You need fund, and we have to do this properly. And I think from overall, we have to be far better here in order to make the society good for people, as your rector mentioned. From AMOS, the center, we have been working very hard to get this up running. So if you go to the next. This is spin-offs from, you see, from CCAS, the first center. And I was not the director there, I was one of the key scientists. But you see here spin-offs from AMOS, where we actually are running out completely new companies. And you may think this is the only innovation, but this is only 10% of the innovation we are doing. The 90 is already with existing in cooperation with the industry. So here, I think we have to be clever together in order to maintain, I would say, the life standard we have in Scandinavia. And we have to work hard. So thank you so much, and again, congratulations. And I must say, I look really forward to work together with you guys.
Thank you very much, Asgeir. I think we have time for some questions, and just a moment, I will bring you up to the audience, if I manage. And yes, so please, the floor is open for questions. If you would like to address any, you can use the microphones that are here. Okay, while, yes, please, Patrizio, there is a microphone here in the middle. You need to open it on the top. Just switch.
Yes. Can you hear me now?
Yeah.
Yeah. Thank you very much. It was a fantastic presentation going through, the needs in ocean science, to the solutions that we have, and also to the societal development in Scandinavia. So, fantastic presentation. I have a question specifically on the ocean science and observation part. So, since I come from DTU and the Institute for Aquatic Resources, DTU Agua, you focus a lot on the needs of operations at sea, but also observations at sea, and with autonomous solutions and also robotics. I was wondering, what is the role of those that are already at sea, like fishermen and aquaculture and transport industry? What type of autonomous solutions that are available already today to fill the gap in observations we have?
Good. Well, in a way, if you're looking to aquaculture industry, to take that, we are very closely connected to many of the main stakeholders in Norway, where actually we are, and if you're going to the different levels of autonomy, as I mentioned. First of all, so in a way, we are helping that and doing that, not as a revolution, but more as a transformation, where they are taking more and more systems in use. So one of the most risky operations, for instance, in aquaculture, if you take that example, is that when the people operating them are going on the aquaculture ring and doing maintenance in an environment which is quite risky, and it could be quite windy and very tough environment, we actually replace that with robots. So in a way, you make the life simply better. So that is one example we do, and we are together also with industry actors are putting more and more instrumentation. So in a way, you could better understanding about fish welfare, but and also pollutions from that, and becoming more efficiency and also in economic terms. So that is one example where we, in a way, are making life easier. But if you go into some, if you take the example of autonomous ships, there we are putting the seaman on land. And there is obviously, you could say, debate going. Are we now taking? Are we taking out workplaces and what now? Well, there will be transformations, and I'm quite sure that, and there are some issues regarding that is crucial, but they will happen anyhow. That is point number one. Point number two is that we are actually doing that. We are creating numbers of new workplaces where these people will be having their skills, but they will be doing that from their homes, and they could go home instead of, at the end of the day, instead of being away from the family for long periods of time. But still saying that, I can foresee many new workplaces, but there is a concern in the society that people that is not having these skills, the truck driver, and not saying anything bad with them, but if we end up in a society where you in a way discriminate people and you're not able to employ and activate all people, we have a huge challenge in our democracy. So I think we should, in our, I would say, inspiration and call it technology, optimistic approach, we should be sensitive to people and which is in a way falling out. Because if that becomes the case, we end up in situations we don't want it. So I think, again, here, this is also a part of the responsibility here. Shifters will come, but we have to be wise, and we have to figuring out how could most people be involved still. And even disabled people can now typically do work they have not been doing before, because we are actually making the work environment better. But I think this is tricky questions, and from my viewpoint, I mean here, again, we need probably help from social science in order to understand more of this picture as well.
Okay.
So, but I didn't answer on all your questions, but I sorry for that, but...
Thank you very much, Asgeir, once again, for being here with us today. And I personally look forward to our collaborations in the years to come to shape a very strong center here, and of course to renew the partnership with NTNU to drive this technological change. Thank you very much for being with us, and good luck for your research campaign. So now we move on with our second talk, and I would like to welcome Professor Mons Blanke to the stage.
Thank you very much. Then I'll have to keep my voice down. Autonomy in Shipping Lab. Now, Asgeir has nicely introduced us to many of the reasons why do we do autonomy at sea. I'm going to talk about a Danish spearhead called Shipping Lab. It's a collaboration as a driver for smart shipping in Denmark. We are funded by the Danish Innovation Fund, Danish Maritime Fund, Orients Fund and Lauritsen Fonden, and we have great support in the startup phase of this program from Danish Maritime and Danske Rederier. Now, it's not all of us who are working with this marine area, so I'll introduce you to the environment first. What is safe navigation? What is the role of a navigator? A navigator takes care not to bump into anything, not to go on ground, observe what is out there at sea you will see signs like this one. This means a fisherman is fishing, so we have to give way to the fisherman. There are rules of traffic called colrex at the sea that tells you how to maneuver when you meet others. At night time, we have indicators for how to pass a certain region. These are light buoys, other buoys do not have lights. At night time, ships are required to carry lights so that we can understand which direction do we meet them in and what are the rules of navigation. The task of a navigator can be extremely complex. A situation like that, with perhaps 300 ships within the radius of attention, is quite difficult to actually oversee. The maneuvering property of own ship and other ships can be very different. You have to take that into account. You just, not like a car where you just turn it. This fellow can be turned, but it will take 10 minutes until it has actually executed a turn. And one of the big concerns in certain waters is that if you are out in a sea kayak, you perhaps don't know it, but you are invisible to radars. So unless there is an outlook that takes care of you and makes sure that to give you a safe way, you might be in danger. We would like to help navigators be able to temporarily do something else on the bridge. That is called temporary unattended bridge. But that would call for decision support. You might imagine a navigator doing something else. A navigator on a ferry is, by the way, also selling tickets out on some routes and perhaps even taking care of issues with passengers who cannot find their way around and. So attention can be focused some other place. It would be a great advantage to have systems that could provide decision support that in a glimpse of a second could give the navigator a situation awareness impression and also perhaps guide the navigator on what to do now. In unmanned operation, small craft on demand, for example a harbor bus, that would call for autonomy and backup by remote control. What is done today is a human navigator using his binoculars, using the radar, combining the radar with sensors, might be able to give this autonomy another dimension because we use electro-optical sensing instead of the human when the human is not there to look out. What is it we want to obtain? We would like to track objects, interpret information, create this situation awareness with great robustness, with great safety in order to reduce the risk. We would like to let a machine implement the colrec rules, understand how are others supposed to navigate, compare with how do they actually navigate. Because those of us who have been to sea have seen, in particular, leisure sailors who have no clue of how to navigate according to the rules. It's a fact that leisure sailors can rent a boat without ever having understood a clue of what the traffic rules at sea are. And in some situations, we would like a human to intercede a computer. But in other situations, we would like the computer to intercede the human if needed. And why is that? Because we see accidents where stress factors or other inabilities to carry out a safe maneuver sends a freighter on the coast of Bornholm, makes a freighter collide with a bridge, and we don't want that. So taking an offspring in what is the human decision-making process for situation awareness, that is At a level 1, a perception of what is going on. Level 2, an understanding. And level 3, an anticipation about what will happen. This has not been invented by us as technology people. This comes from human psychology. What we would like to is to replace, or at least implement, computer algorithms that will do this green circle reasoning. We will go from human awareness to machine awareness. And the methods will be learning-based perception and logics-based understanding. So we would like to have sensor fusion of data from different sources, and I will show you over the next 5 minutes what we mean, what types of sensor fusions, what types of sensors, what types of data processing needs to be made, and how we do it. And from there we will go to decision support in the case of a temporary unmanned bridge, and we will go to autonomous decision making in case of a vessel where the operator is not on board the boat, but there is a backup on shore. The first argument is sea kayak. This is the image of a sea kayak taken from the bridge of a ship. Even with the camera, it's difficult to really observe what is going on here because of the lack of difference in colors in the image. So even for a human, it's difficult. What do we do to investigate perception? In the project Shipping Lab, in the Autonomy work package, we work with radars in different bands. We work with electrical optical sensors, visual, not visible, heat sensitive. We receive AIS from other vessels, knowing that that information can be fake, erroneous, or simply missing. It's well known in the business that fishermen who have a good catch, they of course switch off the AIS in order not to tell anybody else where the good catch is. We of course know position, heading, speed, water depths, and we have electronic navigation charts. This was a Tucumorine boat, which is one of our experiment platforms. The first image was at daytime. The foremast is equipped with all the instruments that I just mentioned. And at nighttime, the situation looks like that. We need to investigate what to do at day and at night, because autonomy has to work 24/7. A W-band radar is also known as a car radar. It's a smart device that works at short range. That is useful for us inside harbors in particular and at close range, 50 to 200 meters. This is the situation as we see it. This is the situation as the W-band radar sees it a few minutes later. You can, for example, clearly see the poles here that you don't want to collide with, and interpretation of these clouds of points has to be done to identify and also collaborate with the cameras. What are these objects? I mentioned the electronic sea chart. An electronic sea chart for those who are what we call in Danish landkrabber, pedestrians who are walking and not sailing. A sea chart looks like that. There are various indications like buoys. This is a light buoy. Some buoys up here indicate the direction of where you should travel. You should, for example, go east of this one in order to be safe. And other marks tell you where you have shallow water and should therefore pass at a certain site, north, south, east or west of the marking. You have red, you have green buoys to show you how to enter into the harbor of Faaborg in this area. So this is the sea chart. And if I press here, will the video start? Yes. So this is own vessel making speed. At Faaborg Fjord, there's one other object. We can see that certain of the buoys are detected by radar. Others are not because they don't have a radar reflector. And interesting enough, a couple of the buoys are here on the radar, but were not on our sea charts. Phew, we didn't update our sea chart before departure. That's a big mistake. But it happens. So this is the kind of information, and sometimes lack of information, and sometimes a little bit of misinformation that the autonomous system and the artificial intelligence has to work with. Assessment of the situation also has to do with how are other vehicles moving in the area. In this case, we are tracking objects using only vision. We can also track objects, and we will do that using also radars, but it's interesting for all kinds of autonomous systems to have backup. What about if the radar for some reason does not work as intended? Then we would like to be able to track the objects alone from the cameras. And reversely, of course. And what you saw there is a neural network classifier that finds an object, gives it a name, and maintains a list such that our intelligent system has a range of awareness within which it knows what is going on and reacts on that. What about nighttime? At nighttime it can be fairly confusing. This was unfortunately accentuated in Norway not so long time ago, where a Norwegian frigate mistook land lights and for lights on a tanker that was actually leaving port. This led to a collision and the sinking of a Norwegian proud frigate. Why is that so difficult? This is an image of the harbor of Helsingborg. Some of these lights are actually light buoys that tell you something, namely how to navigate. And how can a machine understand which light buoys are there and how to react. Light buoys send out a certain signal. They have different types. For example, ISO 3R. 3 means something with a period. This is a neural network, a new type of neural networks that we created in the project, where after observing for a while, the network comes up with a result. This is a certain buoy, and given that we can see the buoy, we can also estimate its position at night time from the camera information, and we can correlate this with the CMAP information. So what we're doing here was perception. Now we need to understand, anticipate, and decide. Objects' properties need to be known. Are they propelling or are they under sail? Traffic rules are different for the two classes of vessels. What are vessels' ability to maneuver? What are other vessels' intentions? What about leisure vehicles? We might give them a little more space and expect the unexpected and expect weird behaviors now and then. If it's a buoy, understand type and context. Understand and anticipate. We need to, for all objects in the region of attention, to make a convex evaluation to understand what will the others do. What should they do? And what are they doing? Again, we must expect sometimes the unexpected behaviors of others. And when unexpected behaviors happen for two different vessels, this is when a collision is at high risk. Let us look at the challenges. This is an overtaking situation. The small ship, speedboat here overtakes us. Okay, then we know what the traffic rules are. Here we undertake some leisure boats, a couple of them. We know what the traffic rules are. We have a ferry in ahead of us. We have a couple of sailing boats and other vessels around. So we know what the traffic rules are. But what happens here? Here is a small, very fast ferry. Approaching, what would we expect here? Those of us, like myself, would assume that according to the traffic rules, he would pass on this side. But no, this takes too much time, and there is space between the two ferries. So what is he doing? Making this crossing. And actually passing us at very close distance. Situations like that are completely daily life in Svendborg Sund. The master on the ferry we were on board did not lift his eyebrow because this is one of his friends and they do this every day. But how should we learn this behavior? That this behavior is actually a safe behavior with very small margin, however, in timing and very short distances between the vessels. How should we avoid that the autonomous system commands a full stop to our own ship? Because then our autonomous system would not be taken into use. So there is a lot of basis of good research in this area. I've given you some examples of what we need to do. Here comes the architecture of how we are doing this. We have a total in Shipping Lab Autonomy work package. We have a cyber-physical system and we have collaboration between no less than 15 autonomous agents inside here. Each of those need to be resilient to mistakes by others, to take proper action if something happens, need to be fault tolerant, as Asgeir mentioned. I think he exaggerated my role heavily, but thank you, Asgeir. So we have autonomous agents who deal with sensors, who deal with information fusion and event diagnosis, detect and handle the unexpected, situation awareness and risk assessment. If we need to, call a replanning of own route in order to avoid collision, avoid grounding, anticipate the path of others, interact with control systems on board, transit and docking control, propulsion control, interact with electronic navigation charts, and not the least, interact with an onboard autonomous supervisor that should ensure us that what we do is safe. There can be implementation issues here. There can be defects in the thinking, in our thinking, when we learn the machine of how to react. And all this has to be cast over here such that this onboard supervisor could call a ground segment supervisor and have remote command as a backup. I would like to acknowledge the support we have gotten in two projects, ASTA Autonomous Situation Awareness for Navigation from 2018 to 2020, and Shipping Lab Autonomy 2019 to 2020, and a long list of people who we are very grateful towards because they paid 50% of the project expenses. Acknowledgements to my co-workers. I didn't do this work, obviously, myself. we are a whole group of people who have created and are creating these results. So you're welcome to come up with questions.
Thank you very much. I'd like to open the floor for a question or two. Then I have one for you, though we work closely on a daily basis. In the actualization of the autonomous ship as you see it, what do you think would be the biggest technological challenge ahead of us and the biggest societal challenge?
The biggest is always a difficult question to answer. But the fundamental challenge for us is to obtain a very safe response. When people work with neural networks and machine learning, in many areas you are satisfied with a recognition probability of 95%. But at sea, that means that 5% of the objects have a risk of collision because we're not aware that they are there. So that's no good. So we work intensively with research on how to robustify these neural networks, how to understand whether they're trained well enough, how to understand in which corners are they not trained, and in which situations will they not be able to perform as they should. On the technology side, I would say we are striving to be as good in technology and to prove the technology, to validate it and see. The biggest challenge perhaps is the interface with the regulatory bodies, how to create something that can officially be considered safe, reliable and useful in the real business, as Asgeir mentioned as key point for technological success. For society, we hope that islanders will benefit for a water taxi on demand capability. We hear about islands that can no longer be populated because the young people are actually fleeing away. But with a cheap water taxi on demand that would also arrive at 11 o'clock in the evening, pick you up after a happy confirmation with your family over at the land and sail you safe home. We think that would be a game changer for islanders. Also transport of goods at times, and we expect also benefit on economy of these ferry routes, because manning on a ferry today is expensive. Sometimes at some routes 3 people on board a ferry have a break with nothing to do of 4 to 6 hours. That is a particular ferry route I'm talking about. And since the 3 persons are not allowed to go and drink beer on the local inn, they play an awful amount of coffee. They consume an awful amount of coffee and play an awful amount of card playing in the time. That could be better used for other things.
Yes, thank you very much. Let's give a hand to the speaker once again. I would like now to introduce our next speaker, who is joining us from Fyn, if I'm not mistaken. Can you hear us, Mads?
Can you hear me?
Yes, yes, we can hear you well.
Great.
So I will now introduce you, just a second.
Yes, please.
So our next speaker is Mads Bent, Chief Technology Officer from Capra Robotics, which is one of the strong emerging realities in the area of mobile robotics here in Denmark. And Mes will give us a talk about mobile robots in the outdoor public domain. Please, Mes, the stage is yours. I will now share the video that you have sent me so that you can have a feeling.
Yes, you started, and I'll start also. Yeah. Thank you. I'm very pleased and very honored to be a part of this. And I'm going to talk about mobile robots in the outdoor public domain. My background in doing this is I have a Bachelor of Science in Mechanical Engineering, I have a Bachelor of Science in Education Science. It might sound weird, but I'll come back to that. And then I also got an MBA in Economy. I've been a user of powered wheelchairs since 1986, so I have 160,000 hours of experience in driving vehicles like that. So what can you use that for? Well, especially when you want to go outside and drive with mobile robots, there are some circumstances that you have to be aware of. We have our robot company in AMOS, Cable Robotics. We are 14 people. And we are developing this robot that we want to get to the market here in the first quarter of next year. Our vehicle is special in the way that it's very precise in the steering. It has good terrain adaptability, long range, and we have a very good patent for it. What you can see here is the vehicle and what the patent covers, and that they got front wheel and back wheel that can turn simultaneously, so it can rotate on the spot. And then it's also very good at adapting to climbing curves, climbing hills, and so on. Our patent covers already, you will say, most of the important countries in Europe, Japan, Australia, China, Israel, and it's in the national base of Canada and South Korea. And the patent covers all kinds of vehicles. I'll just show you a video so you can see what the application that we're working with now can do. We're not doing the final application. We're making a mobile robotic platform. And that means that it's a B2B, and it could be used for a lot of different things. It could be for picking up cigarette butts in the city area. It could be picking up gum. It could be last mile delivery. There are lots of stuff. I'll just let you have a look at this. It doesn't really care if it's on road or it's on slopes, driving on sand. It does a lot of different stuff. Later, we reckon that we will also be doing other sizes of vehicles and also working with putting a trailer afterwards so it can carry even higher loads. This, of course, needs to be legal, and we've been working a lot with the Danish government to get a new legalization in place so we can start testing these mobile robots. And if all goes well, we should be able to do that from the 1st of January 2021. And that also means that actually I have tried to make it similar, because there are a lot of good knowledge from especially driving with with powered wheelchairs, that we follow some of the same rules. That means that on sidewalks you're allowed to drive 6 kilometers an hour, otherwise you have to gear down on the bike lane, and we're not allowed to do that. 15 kilometers an hour would be okay if there were empty park lots, areas like that. So it is a test law. It also needs to be sure that if anything happens, that people that get hurt, if that should happen, most certainly we don't hope that will happen. That the tester would have to be responsible for that. But I think that is also important and also included in the test law is that at all times when you test these mobile robots, you have to have somebody that could take over. And that could be in situ, or it could also be from another place. But again, from another place, that means as we are driving in Denmark and Danish laws apply, you have to be in Denmark. So we need a kind of facility, as we see it, where people can take over these robots. And there would be a lot of different companies working with these mobile robots. It could most likely be a good idea to make this as a kind of service that producers of mobile robots could produce. Yes, and the thing is that even though that these robots have to drive in the street, we of course have to be sure that the navigation is right. And so there are two challenges about navigation in urban areas. We in AMOS, we are a part of the TAPAS system. The TAPAS system is set up by DTU and the municipality of Aarhus, and also the Danish state. But even though you have good GNSS possibilities with RTK at good in the open area, we can have a precision of ±1 centimeter. But when you get close to buildings, you will have a phenomenon called multipath. And that means that the signals that come from satellites tend to skip back and forth between buildings. That means that suddenly you can have a signal that points at you as somewhere else that you really would like to be. What we're trying to do with mitigating that is, for instance, trying to use GIS, the geodesic data that are very, very good in Denmark, and they try to use that as what we would call something called pre-SLAM. SLAM is simultaneous localization and mapping. And that means that before we even drive, we would like to have a good understanding on where we're going to drive. Normally with SLAM, you have to drive the whole route first before you can let the robot loose afterwards. So that's what we want to do. We want to combine visual map with AI with precision. And there are, of course, other safety things that we have to be aware of through geofencing, and we also have to be aware of moving objects. And we have something that we call soft and hard safety that I'll come back to. So another thing that we're also looking forward to is 5G. That's official also due to we should get the latency down. It's not a good thing that if we should have one of those pilots that I talked about before that should help driving the robots. Should look out of the cameras in the robot that we have a latency time of half to a whole second. That would certainly not be helpful. We are trying to keep the AI as simple as possible, and we would prefer to try to use vectographic change the thing that we see onto vectographic, and then compare that to these areas. Level of possible autonomy. Like I like to say, robots are dumber than mice. Mice can do a lot of different things. Robots are actually quite limited to the AI that they're using right now. And that's also to do of the complexity, but also the need to understand the context. What context is the robot in right now before it can use the adequate AI to solve the problem? Well, there's a lot of difference of driving on a sidewalk and a bike lane or crossing a road. It's three totally different tasks. So we have to find out what kind of AI are we going to use here? The top window is a robot in US that, kind of drowned itself, fall into the water due to it was not configured in a way that it could sense that that was a bad way to go. And again, we might think that we know what to do, but there are black swans and there are broken traffic lights, and we might have made some robots that are capable of seeing traffic lights, but what if they're broken or it doesn't work? And that's what I come back to again, that we need a kind of a robot pilot support center inside the borders of Denmark. And now, as I said, I'm a user of a power wheelchair, and a lot of actually other power wheelchair users that could also be pilots in a situation like that, just as an example. But anyway, it's more than that, because when you have these robots out and driving, of course you need hard safety in the way that you don't want the robots to drive into anything. But you also need, okay, sorry, I'll let pass to that. You also need something called soft safety. I'll get back to that, sorry for that. Regarding this of the artificial intelligence, to understand that is when you learn machine learning or artificial intelligence, it's very, the thing that it had to, the computer had to learn is quite what we call restricted. You can't have all these different complexities at the same time. Okay, sorry. Yes, hard safety. The safety, normally we talk about hard safety in the way that you have sensors that will ensure that you don't drive into things, and that's good enough. That's the right thing to do. But another thing that we don't talk that much about is soft safety. And that's actually to make people and animals feel safe when they are near or passing a mobile robot. Like an old lady comes with a rollator and meets this robot for the first time. We want to be sure that she doesn't get scared of it, because one thing is to drive into it, but another thing is that if she gets scared of this robot, might even step out to the car and step out on the road. She might get hit or something. So we're working with these what we call intuitively understandable intention markers. So the robot has to show its intentions in a way that it's intuitively understandable for a person that have never seen this robot before. And that covers a lot of different things. It covers how the robot looks visual. It's not supposed to look aggressive in any kind. It's not to accelerate in an aggressive way. It's good if you can see the wheel turns, because if you can do that, you can also predict which way it's going. It also includes using colors. Some kind of colors will tend to be more, what do you call that? Maybe more unsecure than other colors, and also the sound. That's also very important. And I normally give an example. The place where we had a company before, we were on a large parking lot, and when you had to go out of that parking lot, to the left there was a light, the traffic light right away, and from the right there was the highway, and in the rush hours the lanes were fully occupied. You could not go to the left if you had to follow the normal traffic rules. The only way you can get out was if you get eye contact with some of the car users in the row, and then kind of let you out. And when you have shark teeth and you're not allowed to get out in any other way, then you really have to use the sidecar. That's what we want to do with our robots also. So this is what I would like to say, and then I'm ready for some questions.
Thank you very much. Thank you very much, Miss. I will now bring you back into the room so that people can see you. Just a second. Yeah. Questions for Miss, please? John?
Hi, Mads. Thank you for a very interesting presentation. How, in more details, do you envision that these intention markers could look like and operate from your robots?
Can you please ask the question again?
The intention markers that you're talking about,
Yes.
how would you envision that they would look like on your robots? Would it be cartoon eyes or blinking lights, or do you have any ideas that you would like to share with us?
Yes, we'll certainly like to do that. Our company's name is called Capra. Capra is the main name for goats, and what does that do to that? It has a lot to do it, because a goat is something you might like to pet it, you don't want to kick it. And that's the same thought that we need about our robots, that it have to be serious, not cartoon-like actually, because then people might tend to do something else. And that's also an intention markers. To make something that's friendly, seriously, not aggressive, and stuff like it. It might sound floppy, but it's all covered in the design phase. Also, just a simple thing like a robot, as we see it, has to have a direction, because then you will know what way it's most likely it's going to go. And that's also incorporating our intention markers. Also that it has some kind of eyes that are visible, but not again cartoon-like. It might be camera, just something that okay, I can see it sees me. So now I'm more assured that it will not run into me. Another intention markers that light, the usage of light, of course we would use what we call a blink light for turn light left and right and stuff like that, brake light and headlight for showing also direction. So it is a lot of different things, and we're working with both with University of Aalborg, University of Aarhus, DTU, and even CCAS. And also DTU on these different kind of intention markers, because they are different. Again, sound, lights, colors, behavior, shape. So.
Are you satisfied?
Yes, thank you very much. And if there's time for one additional question?
Sure.
Yes. I would like to know if you could share your ideas of what would become the most important markets for your product. You mentioned briefly surveillance of properties, but would you imagine it being used in any other major market segments?
As I see it, mobile outdoor robots is an emerging market. And it could be difficult to say what especially would be the greatest market. Again, what we try to do is to provide a platform for other companies to build their solutions upon. But I'm very sure that things like cleaning in the urban area would be important, last mile delivery, but there are so many different things. Also, maybe going out or indoor. Right now we're working with a lot of technologies that are looking into security and surveillance. But we're also looking a lot of other places. So, yeah, we're pretty open for ideas. But again, we are the enabling platform. We're not the ones that do the actual applications.
Okay, thank you very much. Let's give a hand to Mes once again. Thank you for being with us today. It's much appreciated. And we also look forward to collaborate with you within the center in the future. Thank you, Mes.
Thank you very much.
So I would like to welcome our next speaker, Associate Professor Joseph Oeman from DTU Management Engineering. Joseph is an expert in risk analysis, among other things, and he will introduce us to the concept of smart resilience.
Thank you. All right, good morning, everybody. Thank you, Roberto, ASTA, Mogens, and Mats for warming up the crowd. I'm taking over here. I'm very pleased that I can finally talk in front of an audience again. So I've been on withdrawal for the last 6 months. So thank you, Roberto, for that opportunity. I'll be talking about smart resilience and what does that mean and what are the implications for autonomous systems. You'll see a few examples of our work later today. We have an autonomous bulldozer in the test arena. Make sure to ask them about the unexplained path deviations. Yeah, that was one of the fun results that came out of that, as well as 2 posters talking about our work on risk and safety assessment of cyber-physical systems, as well as the testing and validation of the robustness of artificial neural networks. So that is on the nerdier side, but we also look at organizational processes. We look at project management and risk management in the context of project management and innovation. All right, I can do this. Maybe I can't, Roberto. Here we go. Yes. Okay, I stole this picture from the CCAS homepage. So we're talking about collaborative autonomous systems today. Now, let me annoy you a little bit and make this interactive. Is that good news or is that bad news? Is this something that we should be excited about, or is this something that we should be afraid of? Yeah? So, excited? The crowd here is excited. I have one gentleman in the back who goes, yeah, maybe a little bit of both. So let's talk about this, maybe a little bit of both here, because to answer the question, is it good news or is it bad news? I think we also have to ask the question, well, you know, what is it that we care about here? And if I put on my risk management hat for a second, there's something that we call the effect heuristic. And that means that if I'm totally excited about the benefits of something that I do, I will, or my brain will do that for me, you know, discount the risks. The other way around also works. If I'm afraid of something, if I think it's very risky, I will also think that the benefits are very, very low. And you may have come across that in your professional career, where you're totally excited about something only to hit a brick wall with someone you're talking to who, you know, is coming from the exact opposite angle here. And public engagement was already brought up. How do we talk to policymakers? How do we talk to the general public? And I think they're having this risk-benefit conversation up front is very, very relevant. So I'm not overly smart, so things need to be simple for me to make sense. And here's my one picture how I make sense of the world. If I have to put it on one slide, this is it. So I would argue that society rests on 3 pillars. The first one is productivity. And we've been really, really digging into that for the last couple of 100 years, and we're very, very good at it. And I'm excited that we're good at it, because that affords us a high standard of living. then for the last 50 years, we've got excited about sustainability, and I think it was about time that we put that on the agenda. The third one is resilience, and I think that is the one where we don't have 50 years to figure out that that is really, really important. In a nutshell, if something is affordable and if it is sustainable, it doesn't help us if it doesn't work reliably. And I think we've talked about risk perceptions in the break. I think we are spoiled in a good way as a society that our energy system works, our food system works, our medical system works. We're not worried about it not working. And now that we talk about collaborative autonomous systems, we have to make sure that we meet those expectations. And I think if we're honest, and what excites us as academics and thought leaders in industry is that, wow, this is great. It's complex. There's lots of new stuff going on, that I can do my research in. And complexity means, a larger amount of components and larger diversity of components and larger amount of relationships and diversity of relationships between those components. And if you're a risk guy, that gives you pause, because what you've just described is a whole new array of attack surfaces of how to screw up that system. So we have 3 goals that we're going for, and that's classic, engineering challenge. What do? You can prioritize. You can pick one of the 3 and say it's all about productivity, it's all about sustainability, all about resilience. I don't care about the rest. And in some areas that makes sense. If you build a survivable, Navy large surface combatant, you want it to be resilient, you want it to be survivable. You don't care so much about how much it costs. There are compromises. You do a little bit of both, but that will also only get you so far. And I think what we love as engineers is to, look at these paradoxes, make them go away, and reconcile them. And that means innovation. And I think that's why we're here today and why we're excited. And I would put the proposition forward that it's not an option to be innovative here. If you want to do this, we must be innovative. We must reconcile these conflicting goals in a positive way. I'm using resilience a lot, so here's resilience on a slide. You see a pattern emerging. It's always 3 things on a slide. That's about where I can still follow my own argument. So we're looking at our autonomous systems being able to do 3 things: prevent disruptions, resist disruptions as they occur, graceful degradation. It's one of the keywords here. And then we want them to be able to recover and adapt. And we've already heard examples from ASTA this morning. The yellow box in the control circle is doing recovery and adaptation, fault-tolerant control systems on a very low technical level. But you can imagine how that also goes up to the organizational level. And could have a long conversation about where we need to put more attention these days. But why are commercial airplanes so reliable? It's because, we crashed a few, and every time one crashes, we have a global process that kicks into gear to recover and adapt around those challenges. Now, the title of the talk was Smart Resilience and something about service for society. So let's take a second to think about what does resilience mean from a societal perspective. So what is it that we care about as a society? And there are different ways of slicing and dicing the critical societal services cake. Here's one. It's sort of 8 areas where we argue if one of them goes down, our society goes down fairly shortly after. So that is things like energy supply, things like water supply. One that I witnessed was, our financial service. One of my PhDs works at Nets now. With my graduates doing risk management for our Dancourt payment processing. And I was in an underground car garage in Copenhagen when that system went down. So people could not pay anymore to leave the garage. How long do you have until people start punching one another in the face? I witnessed it, so I have an empirical data point here. Yeah, 5 minutes? All right. There was be careful with that guy, in a queue. It was about 20 minutes, 20 minutes. The guy in the front of the queue was convinced, no, I can't just drive out without paying. The 45 people behind him were like, yes, you can drive out of here without paying, because we've been here for 20 minutes. So it's great that we have these very rich lives, but we have to acknowledge that there are many ways in which it can go wrong. And the reason it doesn't go wrong is we had a long time to figure out how things work. But now we propose and we like to propose a radical departure and something totally new and something that's never been done before. And we have to ask the question, can we do that in a resilient way? And resilience for me means, well, we're not allowed to never screw up, but it means we're allowed to screw up a little as long as we learn from that and don't kill anyone or too many people in the process. So what are some of the critical hazards that I think are particularly relevant from an autonomous systems point of view? I think we have 4. Cyber threats is, I think, something that people talk about a lot, but I think they talk about it a lot for a reason. Yeah? And that is that we're now looking at a very significant security safety cascade. So what used to be cyber threats where some computer went down is now some computer goes down, something explodes, and people die. Yeah? So if you think that's sci-fi, Google the Triton attack on the national petroleum infrastructure of Saudi Arabia, and you think you're reading a Tom Clancy novel. Yeah? But the attackers had the capability of blowing up the better part of the Saudi petrochemical industry for at least 6 months. They didn't do it, lucky for us, but it was a pretty hairy affair. Yeah? And that is not a singular event. And now we're saying, collaborative autonomous systems, we're plugging in more vulnerabilities to cyber attacks. So is it okay to do that? Well, it depends, I think. And it depends on our capability of keeping the systems safe. We have climate change. I think that we have unprecedented and anticipated disruptions, because how does risk management work? We look at, has this happened before? Yeah? No, so we don't care. Yeah? Our COVID-19 pandemic, it's been 100 years. The nerds knew that this was going to happen, but doesn't mean we spent money on it, take it seriously? No. Yeah? And it's going to happen more with the climate change-induced disruptions. We have the connectedness of our systems. Yeah? I'm calling out our space-based infrastructure here, which is quite often overlooked, of how if somebody denies us access to that, our lives will change quite dramatically. You think your online banking system would still work when the GPS satellites go down? It probably won't. Yeah? Or there's a chance that it won't, because we use these timing signals to keep the transactions safe. Yeah? So that may shut down. And now we're saying, we're going to rely more on that. Yeah? And by the way, we saw the nice hierarchy that ASTA introduced. There are a lot more interfaces here. And if one of them breaks down, the whole thing breaks down. And we have to figure out, I think, as designers of those systems, what are methods to put an architecture into place that is at least as robust as what we have right now. And then what also worries me is the speed of degradation, because of the connectedness of the systems and their global nature. When things start going wrong, they will go wrong real quick. Yeah? And we've seen that the stock market, nice example of the whole automated trading, talking about collaborative autonomous systems. They're there for quite a while, and they've been a pain in the neck to get right. So we have to be, I think, very careful about designing these response cascades into our systems so that the events don't outpace our ability to deal with them. That brings me to my last slide. Smart resilience. So what? What do we need to do? First of all, the bad news, it's not going to be cheap, but the good news is I think it's going to be a lot cheaper than not doing it. Yeah? And I'm proposing to look at 3 areas here. One is people. So I think we have a responsibility to lead the national conversation on those topics. Because I think as people with a technological, the understanding of the nitty-gritty bits of the technology, I think it's our job to contribute to that. Yeah? And ask questions, what are our resilience targets? What cost are we willing to accept? Yeah? Talking about trade-offs. What are our thoughts about privacy and surveillance here? Because it's great to think about a smart city with autonomous drones monitoring everything 24/7, but they're also monitoring me as they go about that. On the process side, I think I would call it resilience management. So what are resilience assessment frameworks when we talk about collaborative autonomous systems? We don't even have established frameworks for safety analysis. It's something that we're working on right now to make effective across sort of the cyber-physical domain. So there's a long way to go for a systemic sort of resilience perspective to be practical. How do we design for it? It's just like other emergent properties of complex systems. It's not just one component that you can tweak and then it's safe or resilient or capable or affordable. No, it's lots of different things that need to come together. And so this is a classic systems engineering challenge, how to design for that particular emergent property. And then our operational processes around it, because it's not just the system, it's also how we design it, the system, and the human processes around it that are informed by those systems and supported by the system. So how do we run that? And then, last but not least, our smart systems capability. So getting back to the nitty-gritty here, what are things where autonomous systems can help us? Real-time situational awareness is a great one, yeah? Because we make lots of bad choices if we don't have situational awareness. And autonomous systems can go into dangerous, dirty, dull areas, and they don't care. Yeah? They will get us the data. Early warning systems. You know, it sounds like a military thing, and it is, but it can also be around sort of climate change adaptation. Right? It can also be around issues in our energy grid that we need to take care of. And then, you know, at the very basic level, the questions around data acquisition, fusion, and analysis. I know we've been doing it for a very long time, but if you're in that space, you know, with the new technologies, let's just put artificial neural networks out there, this is still a very, very hot topic for research. How do I validate them? How do I reconcile competing interpretations of the data done by different analytical systems and make that useful for a decision maker, either a human or an automated system? All right, and with that, I thank you very much. If you're interested in more, check out our website. I should say like and subscribe. I think that's what you do these days and on a webinar. But appreciate your attention, and I already appreciate the discussions that we've had here so far. So thank you. Yeah.
Please stay. I would like to welcome some questions from the floor or from the chat, if any. Then I have a question for you. This aspect of resilience, of course, I see it very central for the development of autonomous systems. And you have presented us that resilience is not only at machine level, but of course should be built across the different layers of course, within organization, and then, of course, ultimately in society. How, based on your experience so far, how far are we into this process? Is it something that is still very new and people have not really considered, or there is, so to say, already something going on because of this emerging awareness of new technological trends coming up?
Mm-hmm. It's a good question, Roberto, and I think the answer is both. Yeah? On the one hand, there's a lot going on around resilience, and for a while. Sort of resilience of critical infrastructure. We've been looking at that seriously for at least 10 years. But what I'm missing is that we start drawing conclusions from that, and that we feed it back into the design process of those systems. And we always treat it a bit of a sort of after-the-fact discovery if it is resilient or not. And then we look at an existing system, oh yeah, we need to tweak it a little. Fine, but I think we can do better. I think, especially if we talk about collaborative autonomous systems, where it's not quite a green field, but a greener field than most, where I think we have the opportunity and obligation to get it right from the start, because everything else will be not just expensive, but also, let's say, detrimental to public support. Sort of imagine you push autonomous systems to support some kind of sustainability agenda and deploy large offshore wind fields because we can now maintain them autonomously, and it doesn't work. Yeah? I mean, good luck getting re-elected on a sustainability agenda sort of next time around. And I think that's our job, that we need to take those insights and start using them now in the design process.
Yes. Please. Yeah, please.
Hello, Jacob from Lloyds. DTU, they have put up for all students, I guess, how to say, an LCA course for all students. So they need to go through and understand the issues about components and lifetime analysis on the impact on society, on resources, etc. I think that's a course that every student at DTU must go through. So maybe one could make a similar course in a risk assessment, or in the ability to understand when you have a system, either as a civilian engineer, building engineer, chemical engineer, or electrical engineer, whatever branch you are in, that that you bring these sorts in your design from the beginning. So again, like the LCA course, this would be a basic course for all students. Thank you.
Should I comment on that? You're putting me in a difficult position here, because on the one hand, I agree violently with what you're saying. On the other hand, no professor raises their hand and says, oh, I want to do more teaching. Yeah? Oh, few do. But I think it's a really good point, and we just have to start reflecting on, are we adequately covering that side in our teaching in general, and then asking ourselves to what degree should that also be a foundational aspect. I don't think it's completely absent, so to be fair, I think there are aspects of it, but I think we can be more forceful and structured around it, yes.
Following up on this, maybe our new head of studies for the Autonomous System Master Program could consider the introduction of such a course. Maybe not mandatory, but we could have an activity on risk assessment, risk design. What do you say, Lazarus?
Thank you for a very nice talk. I strongly believe that this triangle that you have shown us is pretty important, and I think I'm coming from DTU Electro, and we are always so excited about our technology that we want to just deploy it. So in the scale, like good news or bad news, we're definitely on the optimistic side of this. But I think this should be something that we keep in mind. That was actually a brilliant suggestion. I would agree. Also, it shows how autonomous systems is a topic that goes beyond electro, beyond management, beyond compute or space or aqua, and that it's only the synergies, and we couldn't offer this course. So it's actually, I take it as a opportunity for a very close future discussion.
Okay, thank you very much once again. Our next and final speaker before the lunch break is Professor Paul Popp from DTU Compute, that is joining us from one of our lecture rooms here in campus, it seems. Hi, Paul, welcome. Can you hear us?
Thank you. Yes, I can follow. I hope you can hear me as well.
Yes, we will have to tune down a bit your volume because you come out a bit too loud. But while I introduce you and your talk, I'm sure we can get some technical support on the matter. So,
I can also probably reduce it from my computer. Let me try.
So Paul will talk to us about dependable autonomous vehicle architectures, and his talk, of course, will describe what is the technology needed for, of course, developing in the automotive industry in order to make our these type of vehicles once again more resilient and reliable. Paul, when you are ready, we are.
Thank you. Is the volume better now?
Yes, is very good.
Thank you. So yes, I'm a professor at DTU Compute. I also coordinated a similar center, but related to industrial IoT. And now this has become a Nordic University hub on industrial IoT. So I'm very happy to talk to Roberto and the other guys about what it means to run a center and involve researchers. And I really like the current event and how things are shaping up. I'm a computer scientist, and I'm going to tell you a few things about vehicle architectures and how you have to design them and configure them in order to make them more dependable. So I'll tell you a few things about the evolution of these electronic vehicle platforms. What are the challenges related to dependability? Some of these, the big picture has been covered by the previous speaker. Then I'll give you some examples on how this architecture look like in terms of computation, communication. I'll give an example configuration problem, and if there is time, I can go through some projects that we have at DTU Compute related to autonomous systems. So autonomy in many things, in robots, in vehicles, and so on, is realized through a combination of hardware and software. And software has been increasing in complexity. Here you see the increasing complexity of automotive software. It started actually with analog devices in the 70s used for fuel injection and anti-lock brakes. And then in the 80s, and in the 90s, we had things like power steering and stability control. And a lot of the things that are now driving the complexity have to do with some degrees of autonomy. And you've probably seen, and this is increasing exponentially. We have more and more software in vehicles and more hardware. You have probably seen, I don't know if today, but these 6 levels of autonomous driving, from no automation. I think very few cars have no automation today, to full automation, which is the holy grail. But there's also a lot in between. And cars nowadays actually have a lot of autonomous functions which are at the lower level. So I'm going to focus on level 1 and level 2 in terms of driver assistance. But there are applications, and one of the applications that we looked at is where you have full automation, for example, lateral parking, where you don't touch the wheel, the car will park itself. But of course, the risk there is reduced because you're not at high speed on a highway, you're just parking the car. So we have this increased functionality due to increased autonomy. And we have many functions, things like adaptive cruise control, where the car uses radar to keep a constant distance from the car in front. We have lane departure assistance, where you will be warned if you're trying to change a lane, but there is another car there you don't see, or if a car is coming to your lane. Blind spot assist, car may also brake automatically, for example, if there is somebody quickly stopping in front of you. All of these applications are real-time and safety critical. Real-time means that they have deadlines. That is, the correctness of the functionality depends not only on the results of the computation, but also the time when these are delivered. And for example, an adaptive cruise control will have to compute everything and read data from sensors, take decisions, and apply apply commands to actuators within, for example, 100 milliseconds. And if it does later than that, then some catastrophic consequences may occur. These are also safety critical. The previous speaker has discussed about safety. Many of these systems may harm the human life or the environment if they malfunction. And dependability here is not only about safety and fault tolerance that is needed to operate even in case things fail, but also about security and privacy. There are demonstrations of how people have taken, how researchers have taken control over cars on the highway, and they could control the car, for example. And this is also changing the way we develop these electronic architectures for vehicles and how we configure and design the software for them. What we see currently is such a picture where you have multiple networks with over 100 ECUs. An ECU here stands for electronic control unit, is a processor, could be a multiprocessor with some memory and communication. And they are currently implemented in multiple networks in a vehicle. So you have, for example, a FlexRay network if it has to do with the powertrain, a CAN or controller area network if it has to do with the engine or with other body functions. So several types of networks with over 100 such microcontrollers connected to each other. This is what you have currently in vehicles. And the different networks target different types of functionality depending on how, let's say, tight are the requirements. If it has to do with maybe controlling like windows and the dashboard, then the demands are not so high, and then you use a local interconnect network with some ECUs that are not so powerful. If it's about the engine or the stability of the car, then you have maybe other types of networks like FlexRay and more powerful multi-core processors. What we see as challenges is that we have this rapid growth of software functionality that I mentioned, and we simply don't have enough computation performance. There are a lot of ECUs, but they are not powerful enough. They don't have enough memory. And we cannot address functions like autonomous driving, connectivity, infotainment, electric cars, hybrids, and new mobility requirements and cooperative functions with the current architectures. So what we see is that we go from these distributed separate ECUs, and which each of them may be connected to some sensors like cameras or radars, and you have to find some space for them in the car. So you have a separate ECU for each type of function. If you have, for example, something to help you with collision avoidance, maybe you have one ECU for that. If it has to help you with lane keeping, there is another ECU for that, each with its own hardware, with its own software, for example, for doing image processing and so on, and connected to these sensors. So the trend is now you go from these separate ECUs to more integration, where you have more powerful centralized computing inside the vehicles. There is now a trend in computation called edge computing or fog computing, where you have a lot of data center and cloud computing capabilities that are coming close to the edge of the network. You see the same things for vehicles. You concentrate some of this computation power into what looks like a data center on wheels, looks like edge computing or fog computing on wheels. So you have more powerful hardware. I'll show you some examples. You can handle then more software, more complexity. You connect to a lot of these sensors and actuators, and then you have implement these high-level functions using your software. So this is the trend today. And in terms of advanced driver assistance systems, ADAS, these are some of the sensors that are needed. I will not go into detail. So there's a lot of sensors. What is important here, so from radars to LiDARs to cameras to short-range radars, ultrasonics, and so on, the message here is that you have a lot of data coming into the cars from a lot of sources. You have, for example, videos or LiDAR coming in information. And this is a huge amount of information compared to what cars had to process before. Maybe cars were concerned before with things like the speed of the car and maybe to adjust something related to the fuel injection, maybe a few bytes of a message exchanged within the car. Now suddenly you have video that you have to process and you have to communicate within a car. And current architectures cannot handle this amount of data. And that's why we also have new types of communication architecture in vehicles, and I'll mention those as well. And all of these radars are needed to implement these functions that are there on the right, like from adaptive cruise control to traffic sign recognition and blind spot detection and so on. If you want to see how these sensors look like, they look like something like this, and there's a lot of them in the cars. You have, for example, stereo cameras which are on top of the windshield. You have a lot of environmental cameras to the sides of the cars, maybe a front camera, radars, LiDARs, different sizes, scanners, and so on. And in terms of hardware, you don't have to read all the text here. There are companies now, for example, this is a platform called Razer Motion from two companies, Renesas, which is a hardware developer, and TDTech, a collaborator of DTU Compute, a company in Austria, who are developing this integrated, let's say, ECUs with a lot of capabilities, with a lot of processing resources, a lot of multi-core processors, maybe even GPUs for processing video, all sorts of specialized systems on chip with interfaces to video and towards the sensors, for example, interfaces and also communication interfaces for within the car. So this is how such an integrated platform may look like. And if you look at the software platform, the software stack, this becomes quite complex because you have multiple multi-core processors. You may have systems on chip with multiple cores, some GPUs, and they run different operating systems. Some of these operating systems have to implement real-time safety critical functions, so they are safety real-time operating systems. Some of them are for more legacy automotive functionality, like AutoSAR, for example, which is an operating system in automotive. And then on top of these many operating systems, you also have operating systems like Linux if the functions are not safety critical or not real time. On top of it, this you have middleware that is allowing your processes, they are called tasks in real time speak, in real time theory, they allow your tasks to execute. And you have to execute them using some specialized scheduling policies that can provide guarantees that these tasks will fulfill their timing requirements, and all sorts of other requirements. There are many requirements. Imagine, for example, you have a lot of what is called chains, dependency chains from reading from a camera or multiple cameras, moving this information on the network to a centralized computation unit, executing these tasks to maybe some tasks on the GPU to do image processing, executing tasks, and to take the decisions, and then applying those decisions to actuators, maybe to the brakes, to the throttle of the car, and so on. And this is also then connected within the car itself via a backbone. For example, a trend now is in vehicles is to start using some Ethernet variants. I'll tell you about that in a moment, because those are the only ones that have enough bandwidth to run, to disseminate all of this information within a vehicle. Now if you look at, and what the point here is that these are, as you see, quite complex platforms in terms of hardware, software, operating systems, middleware, a number of tasks. There are thousands and thousands of tasks that we execute here. And it's very challenging to design this platform. When do you have enough computation power? And it's very difficult to configure them, because you have to decide, for example, where should the tasks execute, for how long, how do you schedule these things, and so on. And this actually has become an intractable optimization problem, which is very difficult to solve. We collaborated, I'll show you in a moment, with automotive manufacturers to solve these problems, because they don't have good solutions on how to configure these things and to guarantee timeliness and safety criticality at the same time. In terms of connectivity, the trend is that wiring, point-to-point wiring harness, like you see here on the right, has been slowly replaced with multiplex networks in vehicles. It got to the point where just this wiring harness in a vehicle had a weight which was more than the engine, and it had cost which was higher than the engine cost. So it was then replaced with multiplex networks such as controller area networks, CAN, and also specialized protocols for vehicles like FlexRay. But even those protocols nowadays, they cannot handle the amount of information that is disseminated within a car and in collaborative vehicles. So we use, so the trend is now towards network convergence using a variant of Ethernet, which is called time-sensitive networking. This is basically a standardization effort at the level of IEEE, which is extending Ethernet, that you all know, with substandards that provide real-time and safety-critical functionality, making sure that things work even if you may lose some messages, making sure that you can actually have traffic on the network that is that has very tight requirements in terms of latency and jitter. So even you have a global notion of time here to have some synchronous traffic going through the network. At the same time, coexisting with standard Ethernet traffic or streaming traffic, for example. And then you use this Ethernet to connect the different ECUs here that each run different applications that then communicate via this Ethernet backbone. And there are now vehicles on the market that are using variants of this deterministic Ethernet, and this will be in future vehicles everywhere because it's a standard and it's well suited for autonomous functions because it can handle a lot of data in a timely way. Future vehicle architectures will look like this, where you have maybe different domains. For example, the powertrain domain here to the top right, where you have maybe something like CAN, maybe some more specialized CAN that can provide more bandwidth. And they have a domain gateway to a switched Ethernet network that is providing the backbone to communicate a lot of data, especially from cameras needed for driver assistance. More and more, the switched Ethernet will be used in more domains inside the vehicle. Now, let me. I don't know how much time I have. I think I started a little bit later, 30 something. Okay, I'll try to end in a couple of slides because I think we're also delayed. So what you see here is an example configuration. This is what you need to plan in order to run all of these ADAS functions. So you have to decide for each core and for each multi-core processor on each core on each GPU, how are you going to run these tasks? Each of these color rectangles are a task that is running. There's also communication among them. You have thousands of these tasks, and you have to decide typically a static schedule because these are used in safety critical systems before you actually put the car on the market. So you have to decide where to place the tasks and how to schedule these tasks. And this is an intractable optimization problem for which you cannot obtain optimal solutions. So what we do, I'm a computer scientist. I design algorithms that help you to come up with such a solution that you see on the screen that meets all the timing requirements, and you're sure that it will not fail, for example, if you deploy it in vehicles. And this is an example work that we have done. We just got the Best Paper Award at on the Emerging Technologies track at the conference on emerging technologies and factory automation, exactly on this, on mapping and scheduling automotive applications on ADAS platforms. And we use their meta-heuristics, which is a type of solution algorithm that can be applied to multiple problems. Okay, and these are some example projects, but I will not go into that, so I'll stop here. And any questions from the audience?
Okay, thank you very much, Paul. The floor is open for questions. Please, Morten.
Thank you, and thanks a lot for a really interesting presentation. My question is that in the public domain, the vehicles that comes with a long history and has ended up in this architecture for, amongst others, historic and specific reasons from that industry, they will meet the small industrial robots that comes on the sidewalk that we heard previously. I'm curious about the architectures of the, you can say, the old school vessels and the new class vessels. How do they relate, and should they reconsider, and what are the differences between the, you can see, the architectures of the different systems? Is the question understood?
Yes, thank you. In the vehicle area, these architectures are driven by cost. So because you are hoping, automotive is a mass market, and because you are hoping to sell a lot of vehicles, millions of vehicles, even if you can save 1 krona out of your architecture in terms of unit costs, this is millions and millions of kronas over time. So that is driven by costs, and in the automotive area, they were quite. It was quite an interesting development in terms of safety. They wanted not to have functions that are very costly in terms of safety, like you have in avionics. Of course, and then they have a lot of backup systems, like mechanical or hydraulic backups, which are avoiding putting more electronic and software functionality that would increase costs and which would increase, let's say, the risk. So they reduce risk by using backup systems like mechanics and hydraulic. Now, what you see in other application areas like small robots, what is happening there is that you have architectures that are coming from consumer electronics, which are especially designed to be extremely cheap and to have a high average case performance. And in many areas like automotive, where the risk is high if you crash, you cannot use such consumer electronic architectures because you don't know much about how they fail. A lot of them have a very short lifetime, and you don't have a good worst case performance. The average case performance is excellence, but the worst case performance is sometimes difficult to understand. This is even more pronounced in aerospace, but it's also so in vehicles you have specialized microcontrollers from companies like Infineon and Bosch and so on that are not very useful for smaller robots and for other application areas. Where there you go then with more off-the-shelf microcontrollers that are using consumer electronics because they are very cheap and very powerful. I don't know if this has answered the question. I'm not an expert on robots, but I see my colleagues, both at DTU Electro and in Denmark, using typical off-the-shelf architectures, and then something like ROS, this robot operating system, which has some other problems related to safety and so on, but that's what I see.
Thank you so much for the answer. It did answer a lot of it, and I think my end comment was that the two categories of vehicles will meet and overlap at some point. It's just interesting that they will come from such different backgrounds, and I think that's an interesting development area.
Yes, thank you.
Okay, thank you very much, Paul, once again for joining us today, and congratulations for your award, and let's give the speaker a hand. So now the morning session has finished, only 20 minutes late, so we are doing great. The following part of the day, or the next hour, will be spent inside the Autonomous System Test Arena, where a few demos have been arranged for you to witness what is going on here at DTU when it comes to mobile robotics, drones in different domains, and also to enjoy our new baby in the house. So please take your lunch bag with you, and then outside there will be stewards that will accompany small groups from here to the test arena, and then in there everything is settled for you to enjoy. Thank you very much for now. So I would like to welcome our next speaker. So after this hopefully interesting break in ASTA, where you've been able to assess some of the work that we do here on autonomous systems, we continue the day with talking about autonomous systems in agriculture. I would like to welcome Morten Lefbilde, manager at ACO, which will give us a talk about digital transformation in the agricultural machinery domain. Thank you very much.
Thank you. So, yeah, as stated, my name is Morten Bilde. I'm here representing the company ACO, and I'm here to talk with you a little bit about how we are tackling the digital transformation towards autonomy. So, by way of quick introduction, for those of you who don't know us that well, ACO is one of the remaining major global players in the agricultural machinery domain, grown through acquisition over the last 30 years, meaning that we are today a multi-brand company. We also like to think ourselves as being full-line supplier of agricultural machinery, from tractors to implements to self-propelled equipment like combines and sprayers. As a global company, we are, that's a bad picture. As a global company, we are naturally distributed all over the world with both production and engineering facilities in most of the world. In the context of collaboration with DTU, I'm going to zoom in a little bit on my home base, which is our engineering center here in Denmark, more specific in Randers, of all places in the world. What makes this engineering center rather unique, in ACO at least, is that it is the only engineering facility that is not attached directly to a production facility. Moreover, we are not attached to a specific product line or even a specific brand per se. So because of that freedom, we have over the years kind of developed ourselves to become this more independent entity, focusing on research, advanced engineering, and ultimately technology development to support our different product lines globally. So just like our industry and ARCO by and large are going through this kind of transformation from being a provider of steel and iron to become a provider of technology and solutions, so is the say internal competences and focus area transforming within the engineering group, and in particular within our group here in Randers. So just to illustrate that development in a simple way, I made this this chart here showing the growth of our internal resources and competences over the last 10 years, divided between mechanical engineering disciplines and electronic and software as kind of a broad theme. As you can see on the mechanical side of things, things has remained fairly stable over the years, whereas something interesting happened about 5-6 years ago. What happened back then was that we started to approach several Danish universities and kicked off some collaboration, in particular with Aarhus University and with DTU. Shortly after, we also launched our first industrial PhD program with DTU. And only 2 years after that, we were ready to launch the first product generation that was a direct result of this first PhD project. If you want to read more about that specific project, there is a real nice article in the Dynamo from 2018, that is. So with this small example out of many, I can't stress enough how important this collaboration with the universities has been in our transformation. And we really see these collaborations as an enabler to spark and kick off new technology domains. So, speaking of new technology domains, the main focus overarching is automation and autonomy, which is what I will dive into now. So before I go too specific about our effort on autonomy, I want to highlight a couple of definitions that we at least work on within ARCO when we talk about autonomy. So we have kind of two objectives within this broad theme. The first and overarching objective talks about smart machinery, which in a nutshell is about automation of our machines, the operations that the machines performs, not only at the machine level, but also as machines collaborate with each other, and as machinery and operations are depending on each other across the whole cropping cycle within arable farming. The other theme talks about driverless vehicles. Now, driverless vehicles, in our mind, is not, it's not the end goal per se. Driverless vehicles is an enabling technology that will allow us to advance the automation to the point where we are capable of talking about redefining the vehicle platforms. So start talking about taking advantage of not necessarily having an operator on each entity, and therefore move towards larger fleets of smaller units. With all of these benefits that I'm sure that you have probably heard of before, so I'm not gonna dive into that. What I find a bit more interesting, to be honest, is not the end destination, it's more the journey. So that roadmap, by and large, we envision looking something like this. So start over here to the left with smart machines, meaning automation of single entities, single machinery, single processes, towards automation of connected machinery, so looking at field operation from more of a system of systems type of approach. This is also where we can start talk about manned vehicles collaborating with unmanned vehicles, still having the unmanned vehicles being supervised by the manned vehicles. And then towards kind of the end game, if you will, fully autonomous fleets. Now, as a company and as a team in Randers also, we are working on all different elements here. So just by way of example, I'm going to give you an example of each of these. First of all, we have our ideal harvest, which is our automation system of our combines, which is really, by the way, what was kicked off with our initial collaboration with DTU back 5-6 years ago. Then, secondly, as we talk about connected machinery, we have an example here with what we call Guide Connect, which allows one tractor to take control over a unmanned tractor. So basically a leader-follower principle. Last but not least, when we talk about full autonomous units, we have our Saver robots, swarm robots, developed for the specific purpose of seeding. As you can imagine, the overall, path as we move forward is to bring more and more advanced machinery, field operations, further and further to the right of this image here. The combine here probably being one of the last pieces of equipment that will make it all the way to the right, just giving the complexity of the machine and of the process. But what does it take to actually bring a machine and a field operation towards automation and towards autonomy? Let's have a look at this example. Just picking on another fairly complicated piece of equipment or field operation, being baling. So consisting of a vehicle system with a high horsepower tractor and a pulled behind large square baler. So today, as an operator of this system, there is a number of tasks that he needs to perform in order to do his job and in order to optimize this task. As we talk about automation, all of these provide opportunities for us to assist the operator with more or less automated systems. All the way from generating optimized route plans, allowing the vehicle to automatically perform these route plans by controlling the speed and the heading of the vehicle, being able to adapt that global route plan to the specific field conditions you are in, to also detect and react to obstacles. And then one of the important pieces is the actual process automation of the task you're performing. In this case, it's producing bales. Last but not least, monitoring and diagnosis of the full system. So all of these technical layers provide opportunities for integration of smart machine features that optimizes or enables the operator to optimize his operation here. As we advance these technologies, we can imagine that we advance them to the point where we can start talking about driverless vehicle. So to the point where we don't need an operator on the vehicles to supervise the operation. He can do that remotely somehow. When we get to that point, there is, of course, also other elements to take into consideration that kind of goes across the whole theme of unmanned or driverless vehicles. Security and safety being one of the bigger problems to tackle. Now, I said that automation, in our view, is not just about a specific vehicle. It's more about the task to perform. And if you talk about a specific field task, there's a lot of decisions and therefore also optimization and automation opportunities that exist even before you actually go to the field. Kind of high-levelly described here with these decision layers stretching all the way from the strategic planning of actually investing in equipment or farming practices to performing the tactical planning on when to actually perform a task, to the operational planning on how to actually go about it before you can actually execute the task. So it means that when we talk about automation, we're also focusing on automating and supporting the end user with these decisions. Ultimately looking at kind of a seamless user experience across all of these solutions, all the way from the, say, off-board solutions and technologies, all the way to the vehicle for our more on-board solutions. So, talking about the future is always easy because no one can really argue against you, at least not with evidence, because no one really knows, right? And this is also why trying to predict the future and trying to create this nice vision, blue sky thinking, where we have fully autonomous system and technology is not an obstacle, legislation is not an obstacle, everything is possible. That's the easy piece of it. The challenging piece is to understand and define the next step and the next step on that journey. And that's also the interesting challenge that I see. And one of the reasons that this is a challenge is because of the adoption of technology, especially in our industry, is never happening as fast as we think it will, and definitely not as fast as we as engineers would like it to happen, right? By way of example, we see here auto steering on agricultural machinery took us about 30 years to reach to a full adoption of this technology. One of the obstacles here is that the farmers don't replace his entire system with a new system. Any piece of technology you want to offer him have to fit with his existing system somehow. So he only replace elements and replace with new technology. And that's one of the reasons why the adoption of new technology is happening a lot slower than what we would like it to. This is also why, by and large, what we are really trying to focus on is that while we do try to create these nice vision and these kind of goalposts as a point of orientation of where we are heading technology-wise, we are more focused on taking kind of the incremental or gradual steps, making sure that we bring the customer, bring the end user along on that journey. So by doing so, or to do so, we need to really focus equally on both the technology feasibility of the product that we are trying to bring to the market, as well as the customer desirability. And that really applies whether you talk about a small incremental feature enhancement or you talk about a radical new solution. Only by having a good match between those two, you will have a viable business at the end. Which is also why we as engineers, we need to not only focus on the technology development, we also need to focus a lot more on the product design. Making the insights about our customers and the end user as important, if not more important, as the insights about the systems that we are trying to automate in this sense. So with that, I don't know if you have time for questions or.
Well, first of all, thank you very much. I would like to open the floor for questions, if any. Yes, please. If you lift it up and turn it on, yes, you should. There is a button on the top. No, on the top.
Hello, thank you very much for your interesting presentation. I'm a PhD student about to finish actually working in safety and security of autonomous transportation and machinery. We had the small bulldozer in the other venue, and I'm interested in your experience regarding the safety and security of this type of systems and fleet of machinery. In your experience, what has been some of the challenges that you have experienced in terms of safety and security and ensuring that there is not some harmful scenarios that could lead to accidents in this type of system architectures?
Sure, it's quite a big topic, to be honest, but I guess for the moment the main driver is legislation, right? And also to a certain extent lack of legislation and understanding of how legislation applies to our specific domains, which is probably why, for example, mining industries is an area where we see these technology emerge a lot faster, because you can create a controlled environment and you can have kind of safety zones and so on and so forth. We can't do that in our industry. And that's probably the biggest obstacle per se, is that everything we do is out there in the open landscape. We can't put a fence around our fields. So the level of compliance with legislation is a challenge in that regard. Which is also why when we talk about full autonomous vehicles, we do envision that these units have to grow smaller just to be able to implement safety on these machines. Imagine those small saver robots. I mean, they are about this size, right? I mean, if it runs to a ditch, it will just stop, and you can pull it up when you get there. Even if it runs into you, it may make a bruise, but that's about it, right? So it's also about rethinking the shape and form of our vehicles, because taking the other extreme, take the big combine there. If we are to make the combine as is today run fully autonomously, it will be an endless task. Yeah.
Yes, okay. Thank you very much. Once again, Ron, thank you for being with us. I would like to welcome our next speaker, my colleague from DTU Space and the head of the Drone Center, Michael Lindenberner, that will talk about autonomous infrastructure, a vision for the future.
Yes, thank you very much, Roberto. It's really a great pleasure to be here today. I'm one of the lucky persons who've been along all the way in establishing the center, so it's been an interesting journey, and now we are getting ready to harvest the fruits and really start projects and getting some interesting things off the ground here. And what I'm going to tell you about today is actually, you could say, my main motivation for having supported this development of the Center for Collaborative Autonomous Systems. And it's a vision for the future, which ties a little bit into what we just heard before. It is this grand vision, you could call it the end state where we want to be using autonomous systems, and we call it an autonomous infrastructure. And I'll of course get back to that, what we mean about that.
but it's trying to address this issue that we discussed earlier today when Joseph gave his presentation, talking about, is it a good thing that we will have autonomous system, or it is a bad thing? And some, of course, the truth always is somewhere in between, and it's always a question about how we manage things. It's also, as we heard in the previous talk, it's also a question about acceptance. It's also about how humans are able to accept and coexist with autonomous systems. So this vision here is just to try to see where would we like to go, and also getting into some more details, how do we get there? Because as we also heard in this previous talk, I mean, just going from 0 to 100 will not work. So it's like if you want to eat an elephant, you have to chop it up in sufficiently small pieces. So that's what we're going to look at. As mentioned, I'm head of the DTU Space Drone Center, which is not a research center, but it's a coordination facility where we coordinate projects and project activities across DTU, but also with external stakeholders. And coming from the Space Institute, you could say autonomy is in our DNA naturally, because we're used to operate with space systems which inherently have to operate autonomously, as we just got demonstrated this night when the NASA probe OSIRIS-REx landed on the asteroid Bennu and hopefully extracted some samples from this asteroid. So this is just examples of elements to an autonomous infrastructure. We've seen some of these examples before today. Things that are operating in all domains, in the air, on land, at sea, both above and below the surface. And you could also include other domains like space, for example, and I'll get back to that at the end of my presentation. And here you can spend a lot of time discussing the capabilities, the pros and cons, the challenges and the advantages of the individual platforms, their ability to perform something in an autonomous way. And you could say, if you look at it from an efficiency perspective, we assume that when we establish autonomous systems that they will be more efficient than the equivalent in the manned domain. So if we take autonomous system, it should be more efficient than a manned system equivalently. It could be an aircraft, and you could say when you fly on an aircraft, we don't do that very much anymore, but when we used to fly an aircraft, actually, when you're sitting in an aircraft, much of the time when you're sitting in an aircraft, it's not the pilot flying, it's actually the aircraft itself. So we just have to nudge it a little bit to take the pilot out of the cockpit, because 60% of all aircraft accidents, they're actually human errors and not errors by the machine itself. So it will be a bit difficult, and that also illustrates this issue about the acceptance, because it will take some time to get people used to getting into an aircraft where there's no pilot up front. So that's really a big thing in this domain here. So from a pure efficiency perspective, I'm a techno-optimist, I have to admit that. So I think it will work out. I mean, we will be able to design these systems so they will be more efficient, either be it in agriculture or in logistics and transportation or whatever. So it will make our society more efficient. But as we also talked about earlier today, in Joseph's talk, about the resilience, about being able to make sure that this infrastructure will always work, because there are challenges. And just to remind ourselves of some of these challenges in a very concrete way, I will just look to some examples from the air domain, where we already today see some challenges, and that's not autonomous systems. These are actually mainly humanly operated systems, like smaller drones that are used, where you can see that there can be different kind of misuse of such systems. It can either be that it's just because operator errors, or it can be hardware or software failures, so it's just an accident, you could say. But there can of course also be people who with intention want to do harm, so it's a malicious use, and there are various scales of the malicious use that are listed up here. You could say going already from the soft part of it, where you violate people's privacy and take photos of things that you should not take photos of, or you're not allowed to at least, going all the way down to the actual physical attacks where drones can be used for terrorist purposes, or for criminal activities like smuggling something into a prison. And then you would say, okay, what are the challenges dealing with this? Well, of course, there are a number of challenges. You have to be able to detect something is coming your way. Then you have to be able to understand what's going on. You have to identify this system. Is it actually a threat? Should I handle it as a threat? And then if you say, yes, it is actually a threat, then I have to do something about it. I have to invoke countermeasures in order to handle the threat. And typically, as we stand now, we have these challenges where using systems like this, it is quite difficult because they're small, they're hard to detect, the reaction time, and therefore the warning time is very short. And therefore, even though we have different systems emerging for countermeasures against drones, radar systems, acoustic systems, and combinations of different sensor types and different kinds of countermeasures, including also weapon systems like nets or high-power lasers and stuff like that. It is really a tricky and complicated thing to handle. So what could be the alternative? Well, the alternative, it could be an autonomous infrastructure. And here an autonomous infrastructure is actually not looking so much at the individual systems that are part of the infrastructure, but it's everything in between. So you could see here listed a number of properties of such an autonomous infrastructure, that it consists of more systems. All it's obvious, we could say. It's multi-domain, so it's not just things flying in the air or driving on the ground, so it's air, land, sea, maybe also space, cyber, if we are talking IoT. It's collaborative, it's self-organizing, and these are the very important parts. So it's self-organizing, so the autonomous infrastructure will be able to handle itself, manage itself. It will be modular and flexible, naturally. And the last point is very interesting, because if we want to have something that's working and not necessarily is an industrial standard, but actually an open infrastructure where various kinds of autonomous systems can join and leave again, so you have to have something that's open, but at the same time it has to be secure. And when you say open and secure in the same sentence, then something is not really right. But that's one of the challenges we have to face here. This is a model of an autonomous infrastructure where you have 3 domains represented, air, land, and sea. And the idea here is that you're not putting specific systems with specific sensors and specific capabilities at the center here. What you do instead is that you say, okay, what is the task we have to solve? So you put this task at the center, and in the ring surrounding this task, you have various autonomous systems. They can be very diverse, they can have very different capabilities, but the idea is, and that's symbolized here by the small lightnings in between, that they're communicating. So they're communicating and they're sharing information, and they're talking to each other. And this will allow the infrastructure to be able to actually identify tasks. They can also be given a task by an operator, say, please do this. But in principle, they'll be able to organize themselves, to solve the task, to find out, okay, who's going to participate in solving the task, who's going to collaborate, and deconflict to make sure that the others, they do not interfere with the task at hand. And this, of course, will also support the idea of if something goes wrong, if one of the participating systems fails, then it will be able to actually be replaced or compensated by the infrastructure itself. And how does this then tie into the security issue that I raised before? Well, an autonomous infrastructure will be able much easier, much faster to identify that something is anomalous. So something is here that's not supposed to be here, or is acting in an anomalous way, and therefore be able to identify and even maybe neutralize a threat much better than human operators trying to figure out what's going on, what's approaching, what's happening on very short time frames. As I mentioned before, when you have to eat the elephant, you have to chew it up in chop it up in smaller pieces in order to get it down. And from my perspective, I'm not so much interested in the individual systems and their capabilities. Of course, they are the foundation for this. They have to be there, otherwise we do not have an autonomous infrastructure. But I'm more interested in the things in between, the glue. And there, of course, you have issues like navigation, communication, the management part of it, data and traffic, and then the countermeasures part that I mentioned before. And not mentioned here, also things that have been mentioned a number of times, the regulatory part of it, legislation, and also then, of course, very important, the human acceptance, the interface between the infrastructure, the autonomous infrastructure and the existing infrastructure, both physical infrastructure that we have in our society, but also, you could say, the mental infrastructure that we have in our heads, the perception of how does this work, do we accept to work and live side by side with autonomous infrastructure. And that's why I think the center that we are celebrating today, really, because when you look at some of the competences and interest areas for the 4 participating DTU departments, I think we are really well off being able to address some of these enabling technologies and actually get some thorough and robust development in these areas, going towards the vision of an autonomous infrastructure. As you have already witnessed, the ASTA test facility is open now, and it will allow us to do small-scale tests of various elements of the autonomous infrastructure. Right now we are conducting a project together with the Alexandria Institute which focuses on the communication bit, because the lightning bolts you saw around the ring of autonomous systems, they have to be able to communicate with each other, and this drone-to-drone communication is very important, and my good colleague Måns Jørgensen, who is coming with giving the talk just after mine, will present this project afterwards. Then, when you have tested some of the core technologies on smaller scales, you have to scale it up and you have to get it into a realistic environment. And this is where the TAPAS test platform comes into play. It's located in the city of Aarhus, and it's an RTK network, so it's high precision navigation, and it's being expanded with high-speed communications with 5G and other enabling technologies in order to be able to test autonomous system in a realistic urban environment. And my colleague from DTU Space, Per Lundahl Thomsen, will give a presentation of the TAPAS infrastructure later today. So just to finish off, and showing this image here, because as I said, it's not necessarily only land, air, sea, but space also might be a good place to think about autonomous infrastructure. As you know, right now we are seeing a very high increase in the launch of satellites. Elon Musk is launching 60 satellites per launch for his new Starlink communications mega constellation. So the increase of man-made space objects will increase the risk of collisions in space, and these collisions, they will then produce a lot of space debris which will really have a negative impact on our free access to space. How do we handle this? Well, it will be difficult for human operators on the ground simply because of the short time frames, and very, very difficult to overview this huge number of objects that we are going towards, many, many thousand satellites, and then resulting many, many thousands pieces of debris. So yes, artificial intelligence can be decision support, but maybe we should consider try to push the idea, and we are doing that right now as part of the Danish space strategy, to introduce the idea of autonomous infrastructure in space. Let the space infrastructure regulate itself and do the traffic management, because it is much faster, much better, has much better ability to do it on a time scale that will avoid future collisions. So this was my pitch for this grand vision for the autonomous infrastructure. There are a lot of elements that needs to be developed, that needs to be tested, but I think the Center for Collaborative Autonomous Systems is exactly the right place for doing it. Thank you very much for your attention.
Thank you very much, Michael, for this vision about the future. I would like to open the floor for questions. I have a question for you, Michael. The journey, of course, is very long, and the first steps have been made. How do you see the major stepping stones on the way to this ultimate achievement?
Well, I see that all the enabling technologies, they will be developed individually, and the fusion of these enabling technologies will have to have, you can say, it has to have some kind of test setup that will allow us to demonstrate that this will be able to work in both efficient, safe and secure manner. Both to address the idea about the general acceptance, but also to find out how to combine this into our legislation and regulation. This is some of the themes we're always getting back to, but when we get here and we kind of said, okay, we set this infrastructure loose and we expect it to actually do its job in an efficient, safe and secure manner, it will really put some tight constraints on how we manage this. So we have really to think about how do we test this, how do we do realistic test setups that will convince ourselves that this will actually be working.
I have actually another question. You pointed out yourself that one of the interesting points, of course, that we would like an infrastructure that is open, so that, of course, many stakeholders can participate at the same time without, so to say, entry barriers. But then at the same time, security is in demand. How do you think it will be possible to reconcile these two elements?
I think it will be a matter of, when you design your infrastructure, that you actually put it in as a motivation for the individual systems, or rather the people who are designing the individual systems, that it will be an advantage for them to be part of the infrastructure, so that you will say, okay, it is a requirement that if you want to be part of the infrastructure, you have to be open and sharing. But when you're within the infrastructure, we of course have some protocols, we of course have some security, and one of the things about the secure communication Morten will address in the following talk. So I think it has to stem from motivation rather than restrictions, rather than say, okay, we want to limit you, you have to do like this and you have to follow specific standards, but be motivated to be part of the infrastructure because it is for the benefit of everybody. I know it might be too optimistic, but I think optimism sometimes can drive the development.
Yes. Okay, let's thank Michael once again. Thank you very much. I would like to welcome the next speaker. Our next speaker, as already announced from Michael, is Morten Skov Jørgensen, Senior Cyber-Physical Specialist from the Alexandra Institute, that will provide us more insight about how to start building this autonomous infrastructure.
Well, thank you. Yes, so Michael has given a quick introduction to what we're doing. I'm actually trying to, we're trying in collaboration to actually take this vision and try and do the first steps. This is what we call our drone-to-drone communication project. I'm very happy to be here. I'm very much looking forward to going over there and testing it. As we've seen today, I, for one, as a computer geek, are very much excited about this. So just a bit of a heads up before we start. I am a computer scientist, so this is going to be a bit geeky. Fortunately, for those of you who doesn't really care about frameworks and so forth, it's only going to be a couple of slides. So you can fade out and then you can come back. Just a quick warning. So first up, let me just quickly introduce the Alexandra Institute. We are a private research organization, GTS Institute as it's called. Our mission in life is basically to take the newest research from universities and put them into play with the Danish companies. We are the GTS Institute that's focused on software as opposed to some other GTSs. So now you know, let's move on. So our project is actually called the Secure Drone-to-Drone Communication Project. It's a collaboration between Rambil, you probably all know those, a small startup called Miley Robots, and of course DTU Space and the Alexandra Institute. It's funded by the InnoSec Innovation Network. They've been so kind to give us some money to actually do this development here. So I'll start off by doing a bit of a description here of what we're trying to do. You saw the model over here on the right from Michael. I'm going to reuse it as well because I think it sums up fairly well what we want to do. So as Michael said, we don't really care about the modality here. So if they're driving, flying, diving, walking, it does not matter to us. This is actually just a protocol for communicating between these units. And it's not, I put it up here, it's not a catch-all, and the reason why I put it in here is just to be a bit humble. I don't believe that what we do here will be the end of time. It cannot solve every problem there is, but we believe it's a step in the right direction for that we can actually start to utilize these autonomous infrastructures. I've also put, I've kind of read a lot of sci-fi lately, and you can probably see it here, encrypted swarm communication for the collective hive mind. I think maybe that was, I don't know if that's a Neil Stephenson quote or whatever, but it's basically what we're talking about here is multi-agent systems that can communicate and they can do it in an encrypted way. And as I put next, and I did this presentation a couple of weeks ago, and I got kind of apparently it's a bit controversial to say that it's hardened from the software pirate world. But what I mean is we're using the peer-to-peer principles here, and for most people when you hear the word peer-to-peer you think about Napster, BitTorrent, and whatever, and so of course you think about pirating software. That's not a good thing. I'm a software developer. I do not like pirating software, but there is one good point here, and you know, it's been hardened from being in that world for so long. There have been state actors for many years trying to shut down these peer-to-peer networks, and they haven't succeeded. So why not take a cue from these guys and actually try to use the protocol for something that's a bit more, let's say, productive. And also, I Googled it the other day, and it was actually also used in the Catalan independence referendum, where the Spanish government tried to shut down access to information. And the independence community down there used peer-to-peer to circumvent the censorship. And that also plays into the fact that it's actually used as a Wikipedia mirror for enhancing access to information that state actors don't want you to have. So, you know, it kind of sums it up fairly well, right? It is a resilient protocol that can be used to circumvent censorship and circumvent breakdowns. If we look at our more specific, what we want to do here, I have a slide here called organization. So why do we want to use peer-to-peer, and why is this exciting in the context of autonomous systems? Because we don't like pirating software, that's not exciting in itself. And I think there's a couple of reasons for that, and I believe one of them is enhancing the resilience. If we actually have a breakdown today, at least for most people's part, if you have a breakdown in either an agent or in your control stack, you lose control. And for most of the time, the autonomous systems are programmed to just do a dead stop, because this is a potential dangerous situation. And you know, in a sense, I agree with this. But what we're trying to do here by utilizing this protocol is to have the swarm being able to organize itself. And don't really care if you have a breakdown, you can still fulfill your mission. So one thing is if the C2 or if a fleet management system breaks down, but the other thing is if you have an agent that breaks down and the system will actually do this reorganization bit. I tried to draw it up here. As you can see, this is not my strong point, but I think you get the point here, right? That number 2 breaks down and then 1, 3, and 4 reorganizes. I do apologize for the lack of artistic quality here, but I hope you can live with it. The other thing is that, you know, we try to utilize excuse me, the features of all the agents, so of the different agents. So again, we don't look at the hardware or the platforms in themselves, what they can do. That's something the system organizes. We actually basically put out a mission that says do a sweep of this field here, and the system chooses the agents that can actually participate in this mission. So, you know, it could be flying, driving, or whatever again. And also, if an agent has some special hardware, we might want to take that into account as well. So we've heard a lot about machine learning algorithms, deep neural networks, and so forth today, and that's all very good. But I think everybody, or most people in here at least knows that these algorithms are very much energy thirsty, to put it mildly, right? So you probably don't want to have too much machine learning running out on a battery-driven agent, because at some point it runs out of battery. So maybe we want to utilize the fact that you can have a basic IoT unit on what do you want to call it? Fixed power lines that doesn't have the battery contingency, so we can actually utilize that. So basically have the machine learning algorithm running on a unit that's connected to a power line. Again, you can just move the data around, the swarm takes care of it itself. Damn. And the last part I want to put in there is it minimizes the network latency. This is meant to run on its own, not on its own network, but it's meant to run on the same subnet. So instead of us trying to send the data up to a cloud platform somewhere, we don't know where, it could be in Frankfurt, it could be in New York, we actually try to utilize the fact that we can put the agents inside the network, so we minimize the latency going back and forth. Again, it's also about resilience. If the internet breaks down, it does happen. You know, we can't connect to our cloud provider, we're kind of screwed. But in here, we have control of it. We know where it is, and we know it's in the swarm, so we can always access it, and we can access it fast. The other part is I want to talk about is the context. So this is actually taken from a slide I used earlier for the Homeland Security Conference, where they wanted to know, so what can we use drones for in a security context? And as Michael said, all the agents know about each other in the swarm. So again, you can actually use the inverse, that if they detect a unit that's not part of their swarm, then it must be well, maybe it's an intruder, but at least it's somebody not supposed to be there. So if you have these agents flying around, let's say a harbor, and they suddenly spot a drone up there in the air together with them that they don't recognize, they can like point up a flag and say, hey, there's something wrong here. You could probably program them to just ram into the drone or whatever, but that's not the purview for this algorithm here. And you can actually use any types of data source of sensor in this network. I've listed a couple of here, RGB, thermal, radio, whatever. And it doesn't really matter, we're quite data agnostic. We try to move the data around inside the swarm by just breaking it down into byte arrays, so it's easily to utilize in different settings. So, if you want to do some image recognition, you can do that. If you want to do some detection of particles in the air, you could do that as well. We just facilitate the movement of the data around. So this is probably the slides where some of you may be able to fade a bit out. Now you're warned. I'm just going to talk a bit about the technology because I think it's actually quite fascinating what we're doing here. I've tried to list some of the technologies we use here. This is just the basics. We use Golang, the programming language. It's very efficient when it comes to concurrency. We use libpeer-to-peer, which is an open source framework for doing this communication. We're building on top of that. Again, we don't try to develop everything from the bottom up. We actually try to utilize what is already there and what is actually available to us from the components outside. And libpeer-to-peer is actually open source. It's developed by the IPFS community, and that stands for Interplanetary File System. I still don't understand the naming, but it sounds pretty cool. These are some of the guys who were participant in actually developing some of the early peer-to-peer protocols I mentioned earlier. So they do have a bit of knowledge of what they're doing. It's actually, I thought when I started looking into this, I thought, okay, so this is only some geeks in the dark corner of the internet trying to figure out how can we pirate software without being caught. But it actually dawned on me when I drove into it that it's actually being used by some quite big names. Microsoft Cloudflare and the Brave browser is actually using this technology for some of their works. And I think that's pretty interesting. It just shows that this technology is not just for a subset of people, it has potential. And historical context, the internet was basically a peer-to-peer network to begin with. We just added this server client terminology on top of it because, I don't know, it's probably easier. Then we use ROS, I guess most people in here know that, and we utilize 3JS, which is a visualization tool, and Unity, the game engine as well. I'm just going to go for a quick talk down technology lane here. Let's start at the bottom. So Unity, most people know this as a game engine. I think Assassin's Creed is probably built on top of it, and some more games I can't remember. But we use this for visualization and simulation. Rambøll, one of our partners in the project, is building complete 3D model of Copenhagen in Unity, and we're going to use that for doing simulation and seeing how it actually works in a simulated setting. And of course, some visualization as well, because Unity does look pretty cool when you look at it. 3JS, which is a more low-level visualization tool for browsers, we're going to use for actually looking into the protocol, try to debug. Basically, it is kind of hard to see what's going on when it's just sent data between the agents around the net. So, we want to have some visualization so we can show what's actually going on. And then libpeer-to-peer framework. I just mentioned some of the good stuff I like about it. It's TCP based, so basically when we're on a network, we don't care about the hardware stack, we only care about the software level. So as long as it's TCP connection is possible, we're all good. We use private public keys for security and authentication. We use a pub/sub mentality terminology, which is similar to what you see in ROS. Basically, you publish to a topic and people subscribe to it as well. And we utilize their gossip protocol, which they have developed, which is shown to mitigate the data through the network, not directly from one to another, but actually through hubs, through the peers. And they have a guarantee that data is being sent to where it's supposed to go. So just let me end up with a bit of example here. We call it Where's Waldo? Most of us probably know him as Holger, at least us Danish-speaking people. But we want an example of what we use here and what we're going to hopefully show off in a month's time is how do we find Waldo? So in an urban environment, we want to use some different modalities. We want to use flying for the overview. We probably want to use some driving units as well, just to get under it. If it's down a tunnel, if it's under a bridge, somewhere where drones are not that easily going to go. And we're going to use some human detection machine learning inside the swarm as well, because we want to detect Waldo out there. You know, we want to have some cameras out there, some sensors. And that's, well, yeah, sorry. We actually we utilized the basic REST endpoint for modality. So it's not completely inside the swarm. You can easily swap this out with different algorithms you want. So the example we kind of imagine in the flow is that we have one agent up there, agent B, who's going to break down. The swarm communicates and they agree, so agent B is gone. We need to reorganize. They recognize one of the agents as the one who has to do the reorganization. It could be basically all of the drones or agents in the system based on some parameters that we set. And after that's done, he sent as the chosen one sends out the mission to all the other agents in the swarm, and they agree on continuing their mission. So if agent B has already covered an area of, let's say, a building or a city, the other agents are not going to do a sweep of that area again. It's going to be tagged as being already looked at. So you try to utilize and just the different drones and different agents and continue the mission afterwards. So, you know, try to do it a bit more efficiently. So last up, I'm just going to do a quick bit of commercial stuff here. We're actually going to do a theme day, as we call it, over at the ASTA facility on the 24th of November. We're going to do a physical demo of this, so we actually believe that it is mature enough now to actually try and have some hardware out there and flying and driving around. And we're of course also going to do a virtual demo, and there's going to be some talks and discussions. So, you know, if any of you are interested, please let me know, and I'll send out an invite to you. Thank you for your time.
Thank you very much, Morten. If there are any questions?
They're looking forward to the coffee break.
Yes, of course, but we have time. In the development of this protocol, what has been, you have put a lot of emphasis in the utilization of this peer-to-peer protocol. Have you, so to say, assessed other alternatives, or what have you driven you ultimately to choose this, so to say, specific type of communication protocol?
Well, it was kind of the purview of the project to use peer-to-peer algorithms, but we decided on that after looking around, seeing what was out there. And basically, when you talk about network communications, you have two ways of doing it. You have peer-to-peer and you have client-server. And as we want to do here, we have agents flying around, and they are peers inherently, so we wanted them to communicate directly, hence the choice of peer-to-peer, sorry. And that was the reason why. We also looked into, and I mentioned that some of the work done on peer-to-peer terminology has actually been done over many years on a fairly heavily stress load. And we thought that would be a great inspiration to work on that, because, you know, if you can withstand the combined might of the EU and the US and still continue your network, you know, you got something going on there. You know, you just have to realize that.
I have another question concerning the aspect of, let's say, safety, security, fault tolerance. Features, so to say, to detect malicious intrusions are already built in, is something that will be added at some point? How do you see this challenge?
So to detect adversaries?
To handle malicious intrusions, not necessarily an extra drone, which of course is not a part of the formation, so we know, but so to say, somebody trying to, for example, take down the network.
Sorry. So if we start with the first point, if we want to detect an adversary, it could be a person, it could be a drone or whatever, that's not built into the system as say, but you can add it in the configuration file that this is a point of interest that you want to handle. So it's just part of it. But of course it's not core part of it, because that's a communication protocol, which is something else. If you go over to looking at attack on the network, well, you can always bring down a network. Like, we can't do anything. If people are badly enough wanted to take us down, they'll take us down. But again, by utilizing peer-to-peer and utilizing this hops over peers. It's also a bit more resilient than using classical client-server terminology. You know, if you're using client-server, you know, if I take down the server, the system is gone. Can't do anything about it. By utilizing peer-to-peer, and they can skip around inside the network, they'll just route around the error issue like the TCP/IP protocol does in its basics, and just mitigate the error. So we can never make it 100% safe. I think we can all agree on that. But you know, I think it tops a level on compared to some other systems.
Yes. Okay. More questions? If not, let's thank Morgan. So I would like to welcome our next speaker, Professor John Pauline Hansen from DTU Management. Now we change once again topic. We go from the autonomous infrastructure to research in human-robot interaction here at DTU. We look forward to your talk, John.
Thank you. Yes, I was educated at RISO some many years ago in a group that specialized in human-machine interaction. And in the meantime, this has spread into becoming human-computer interaction and now recently human-robot interaction. I have a background as a psychologist, so I am very interested in that interface between humans and complex systems, and how to assist humans best in keeping an updated overview of what's going on in the complex systems and making the complex systems more competent by having this human operator to back them up. When their artificial intelligence fail, we can then kick in some human intelligence. We all know that autonomous systems have been working really well for a decade or 3 now in shielded environments like a factory, but it's a completely different ball game when we move out to the wild. We see autonomous or semi-autonomous cars being tested, and we see more and more features that we as drivers appreciate, but this well-known figure clearly illustrates that, well, we are somewhere between assisted driving and partially automated driving, while the tipping point for this industry is here between partially automated and highly automated. And I believe the basic takeaway point from my talk today would be, well, if we can't sort of just jump from today to the tipping point by technology alone, we could probably think of introducing people to make that gap. And then comes the question, how can we do this in a feasible way where this becomes cost efficient, safe, and so on? A lot of hard lessons have been learned when autonomous systems fail. These 2 examples is somewhere here, both of them related to Danish technology. On this side over here, you see a guy working on a campus in University of California, doing nothing but helping the transportation robots that Janus Friis is heavily investing in and developing, when they get locked up somewhere in the corner of the campus. And the basic statistics says that up till now, half of the pizza deliveries out on the campus need him to come rolling on his Segway to help the robot out. So there is room for improvement here. At a local hospital, Herlev Hospital, they spent tens of millions of Danish kroners to have a huge installation of transportation robots in their basement. And it's been standing there now for more than a year. I don't know yet if it's up and running, but the Main problem being that, well, it was efficient transportation system until humans started being down in those basement tunnels also. Then it got so confused that they stopped and they could not learn how to interact with the humans. And this is partly referring back to some of what Ms. Bent said earlier on this morning. How can we make these robots show their intention and have some kind of simple interaction with people that meets them? We have been collaborating with the Danish facility management company ISS, and they have invested in quite a lot of autonomous floor washing machines. One of the first things that they realized that these robots are not really as autonomous as they would have liked them to be, because once they get out on the workplaces, people want to interact with them. And this goes all the way from just sort of playing with them, testing how clever are they by sort of walking in front of it, to actually obstructing it, closing doors in front of it, putting stickers on its camera, and so on. So we need to take all of this psychology, the social context around the autonomous systems into considerations also. How can we introduce a fleet of robots in a company where there will be people in such a way that the people accept them as colleagues, or at least smart equipment that they won't mess up with? That's one of the research questions that we have been addressing. Now, one way to do research is to take extreme cases, and I'll come back to that in a few minutes, but before that I would point at a Swedish project with a lot of emphasis on this person who is the driver of this remote truck. It was demoed first time in the Mobile World Conference in Barcelona. He could, by a 5G connection up to Göteborg, sit and control this autonomous truck that had been driving by itself all up to the final destination, and then he would take over and make sure that it would back in and be able to deliver its goods. So the business model of this company is that they will have fleets of these trucks driving down the highways of Europe, and then they will split out, being taken over by an operator somewhere that will then do the difficult parts of the last driving. This raises the question of, okay, how can we make sure that this person is actually competent in taking this on his shoulder right now? How can we ensure that he is not intoxicated? How can we make sure that he's actually the person that he identifies himself as being? There's a lot of issues here to be raised when we want to make these smooth handovers between autonomous systems and operators. This is also what was addressed within the maritime domain. How can we have remote ship navigators that would have the responsibility of controlling a ship in an open fairway? Now, when we design this kind of human-robot interaction scenarios, we like to take extreme cases, because this is really what's going to provoke new ideas and make us think out of the box, so to say. One case here was a severely disabled patient, not that patient on the picture you see here, but a patient with a serious disease, amyotrophic lateral sclerosis, that completely paralyzed this person, and he would very much like to be able to go around, and we've been working with this patient for many years, so we came up with the idea, maybe you could try then to use the last part of your body that you can actually control, namely your eyes, in order to control a robot. And I would like to show you just briefly how this works. Let me see, how do I start this? Yeah. Now what we do here, we put a head-mounted display with built-in eye tracking on this person's head, and now it's actually the eye movements of this person that controls where the robot is going to drive, not by setting waypoints, but a continuous driving principle. So you see he looks over there and then drives the robot in that direction. And in Unity we built this prototype interface where he can then call up, for instance, a typing interface to send a message to the person he's going to meet with, or send a PIN code to enter a door that he's going to pass through. We had a small map. This was built by Alexander Alapatide at the Alexandra Institute, also in Unity. And on this map, he could then now set a waypoint, and by the collision avoidance systems of the robot, it would be able to drive down to that particular waypoint that was given to it. At that point, the operator would then again take over and be able to drive it into a manual mode. And in a manual mode, he could then turn around the camera as he likes to. If he's looking to the side of it, it will turn just slowly. Actually, you don't notice this turn because it feels really natural. This was at a conference a year ago where some of my students, or 2 years ago, they developed an interface directly from a wheelchair that would convert the turnings of the wheels into steering the robot itself. And the very sort of interesting thing was that everybody can do this right away, and you actually get a bit confused when you take off the headset because you were just over there being the robot and now you're back here in the seat. It's a really sort of captivating experience of you being embodied somewhere else, namely in that robot that you control. So next step, we went out with the Alexander Institute and tested this at an institution, people who are full-time wheelchair users, and my God, they were so good at driving these robots around. So this is actually what made us discuss with Mads Bent. Could we take advantage of that experience? Like Mads, he's been so many years in a wheelchair, he knows exactly how to drive these robots. Could we take advantage of that and suggest that we educate some of these wheelchair users to become the first generation of pilots for mobile outdoor moving robots? They have a lot of time and they would really like to be included in the workforce, I can tell. This is a project we demoed during the launch. It's a EU project where we are supposed to develop AR and VR exoskeletons that can help people recover from a brain stroke, so it will assist them in their daily operations, doing a little bit of that extra movements they need to be reminded on how to use their right hand for brushing their teeth, for instance. And one of our contributions to this will be that we'll focus on building a digital twin that would know what is this patient capable of. So how much extra force do we need to add for this particular person? This is the idea of a digital twin taken from Industry 4.0 over to become a personalized digital twin of a patient. And it could then become an in itself autonomous system that would try to adjust what would work best for this patient and do simulations on how to optimize on the extra force that it needs to push in to help this patient doing the motions right. You probably all saw how we could control the motions of a Lego exoskeleton that we made for just prototyping this. This is not how it's going to look in the final industrial version. The Icelandic company Usur is part of this project, so they are going to build the exoskeleton. But we wanted to have something that would make it possible for us to work with this integration between Unity and some cheap exoskeleton that we can just hand out to master students and let them go home and play with. We take heavily advantage of that machine learning component of Unity that makes it possible for us to integrate and communicate with the exoskeleton. Last example here of a recent project that we do with DTU Compute. We got funding from Synoptikfonden to develop the next generation of Vision 8 systems. So there are a couple of Vision 8 systems out there that are specifically meant for people who have low vision, and some of them are really bulky. They have sort of a hard load of hardware, software costs that makes them unachievable for quite a lot of people that could really benefit from these systems. So what we have convinced the Synoptikfonden to support is an endeavor into building an open digital platform for Vision 8 systems that have this sort of base of the common belief that in a few years big companies like Apple, Amazon, Facebook will develop this smart glass that will make it possible for us to do these digital transformations of the visual field in front of the patient. Now, our special we have already done a couple of proof of concepts here, taking in the visual stream to a pair of VR glasses and then amplifying the borders makes it possible for people to see structures here in their environment that they have never been able to see before. And when we tested it out in home with some people with low vision, they really appreciated it. One thing that we discovered was that when we had left their home and they wanted to try it out, they couldn't find a pair of glasses that we had left with them. So we had to come up with an idea of how this could respond to them calling for where are this pair of glasses right now. This is the kind of insight you'd only gain if you actually produce an early prototype and go out and test it with people. Now again, the idea here being that we'll build a digital twin of the patient. We would train this digital twin with information on how do people with different kinds of low vision move their eyes around. This is actually what we have an expertise in, tracking eye movements, and we can do that from more and more devices. Now it's built into virtual reality headsets and will soon be built into smart glasses. So it's a free sort of sensor information that we can build on, knowing that this person never looks into this area is probably a good suggestion that this is a blind spot for the patient that we should avoid or somehow compensate for. And we can also have people with normal vision doing the same kind of daily task like making a cup of tea. And we can have normal vision people wearing these virtual reality glasses with video streams in and simulate that they have this kind of vision problem that we observe among some of our patients. And all of that being collected in a database and modeled for a digital twin that would then be part of this digital platform assisting people with low vision. I guess this will conclude my presentation.
Thank you very much, John. Very inspiring and giving the opportunity to see how technology can really help the life of people. Is there any question from the floor? Jakob first, I guess, and then Alexander and Silvia, if time allows.
Very short. Is it open, this one?
Yeah, just press on the button.
You were saying that in terms of these classes or intended classes that you would collaborate with Apple and so on. I'm thinking about we are in the Osikon setting here today. We have 3 very strong hearing companies,
yes.
hearing aid companies.
Yeah.
They should be in the business.
Yeah. We are in a dialogue with these companies also, yes. Thank you.
Alexander?
Thanks for the inspiring presentation, John. I'm especially fond of the approach of using people who otherwise have some difficulties finding jobs to help with this new, quite large opportunity of assisting autonomous robots in the world. I know in the past you have tried to be in contact with different organizations and try to get some funding for that. And I was wondering how it's going. Have you received any, or been in contact with any, for instance, ministry or some other high-level instances that could see a benefit for the Danish society in particular? Because I think there is a great potential there.
Yes, thank you. Yes, we have sent in a couple of applications now, which have been let down because we can't sort of prove the business model yet. But I actually supported Max Bent when he approached the new Minister of Transportation and wrote the minister a long letter arguing exactly what you just said, that this could become a new job opportunity for people. And so did Max Bent. I got a long reply back from the minister, but he did not. So I think we have a new sort of political situation now, and our current government, they put a lot of emphasis on this. So I'm hopeful.
Hi John, thanks for your presentation, very inspiring. I will have many questions, but just only one. Regarding the example you showed of the robot at Helio Hospital, you said that it was removed because it wasn't able to communicate with the people, right?
Well, it's not removed, it's still waiting to become operational, I think, yes.
So my question is, let's imagine that the robot was able to communicate with the people, was perfect, no? Do you think that people will have accepted that? And if not, what as roboticists we should take into account in order to increase the acceptability from people? Thanks.
I think it leans towards the research field of social robotics, and they have a lot of ideas that, for instance, if you put cartoon eyes on the robot, or you have a real person that when you call the robot will respond to you, and this real robot, or real person, he could be in charge of 100 of robots, just he would have to announce himself. But also, as Matt said, it's sort of being able to stop and do a little bit of dancing with people before you pass them, and not just sort of roll them over, right? So there's a lot of tangible things here, very delicate kind of social interactions that we should teach our robots. Yeah.
Okay, let's thank the speaker once again. I would like now to introduce our next speaker, Associate Professor Sven Carlsson from DTU Compute, that will tell us about the opportunities of high-performance computing for autonomous systems. Sven, can you hear us?
I can certainly hear you. Can you hear me?
Yes, we can. Welcome, and thank you for being with us today.
Thank you. Thank you. I'm sorry for not being able to be there. I'm not sure whether you can also see my video or if that is set up. Excellent. So I think this is great. So let's stick here. So I'm very happy to be here. I'm very happy to support Roberto and the center and this very exciting new endeavor and this exciting inauguration, or what to call this, of the center. So I'm Sven Karlsson. I'm an associate professor at DTU Compute. And as Roberto said, I'm going to talk a little bit about high-performance computing, because I'm a high-performance computing person. And I'm also going to talk quite a bit about how you can leverage high-performance computing in autonomous systems. But first, given that I'm a high-performance computing person, I need to talk a little bit about high-performance computing. So probably you're all aware that a lot of interesting things are happening with high-performance computing today. Some of it relates to autonomous systems, some things do not. But I'd like to highlight a few things that makes me very proud as high-performance computing researcher working in this field for many decades now, is that now we really see, and I feel also that the general public see the need for high-performance computing. We see the community come together working on different types of vaccines and different types of surveys and modeling of the old famous COVID-19 virus, trying to see if we can find any solutions. You may know that Fugaku, now the world's fastest supercomputer in the world, actually was put into commission early, 6 months early, and was exclusively used for COVID-19 research for many, many months for free in order to serve the society. And we also do a lot of work on EU level, where we're now starting to look into building a digital twin of the Earth for sustainability and environmental research. So a lot of exciting things with HPC, and I'd like also to highlight that DTU is involved in many of these things as well. So I hear many of you screaming, at least those of you that are close to a mic, that what's going on here? I thought this was about autonomous systems. So I would like to get to that point. So I'd like to point to a couple of things that I work together with various friends, colleagues, both at DTU and elsewhere. First, I would like to talk a little bit about some work that friends of mine at the university, Lucas, Patrick, Stefan, Kalle, Liang, have been working on, and I've been engaging on the sidelines here a little bit. So here is a table. If you look very carefully, it's going to be evident in a moment. You actually see a small drone. So let me run this video. I hope you can all see it well. At least I see that you can see it. You see the drone taking off, flying about. What's interesting here, and I like to point to that this drone knows nothing about the room. It knows that it should take off. It knows that it should fly about and come back to where it took off from. But it knows nothing about the room. It knows nothing about surroundings. And it's currently, as it's flying around, mapping the environment and trying to understand where it is and trying to understand where it can fly. And it does this, if you wish, in real time. And soon you will see this drone identifying the landing spot and going down for landing. And pretty soon it will land and turn itself off. So this is done entirely without any kind of assist. And this requires a lot of compute resources. I think everyone will agree that this is indeed high-performance computing. So let me give you a couple of more examples from what's going on here. So you may ask yourself, okay, I get it that this drone needs high-performance computing for this particular task. But what else is there? I mean, I would argue that high-performance computing is needed pretty much everywhere that we have autonomous systems. And I think the prior talk very elegantly described some of these scenarios where high-performance computing is indeed necessary and also supporting the well-being of many, many, many people who are being challenged. So I would again say that all autonomous systems need HPC into some capacity. I see HPC as a fundamental enabler for many technologies. Further, HPC technologies themselves are used across the technology stack. So why is this so important? So let's just go back 2 years. By technology, these are the Stone Ages, pretty much, right? So in 2018, a self-driving car generated about 6 gigabytes of data every 30 seconds. And it used about 2.5 kilowatts of power just to do computation. A lot of things have happened since then. And things are better now. We can have probably self-driving cars at lower compute power than this. But still, we have a massive influx of data, and we need to deal with it somehow, right? Another further reality check before we go into more details here. So coming back to the drone I showed you, if we are to do this on the drone, I must confess that we cheated a little bit. Sorry for that, we did. So if you look at the actual compute needed here, it needed somewhere in between 10 to 50 watt of computing power. This is somewhat equivalent to a low-grade desktop computer, certainly more than a laptop. And we need actually, in order for this to work well on an actual drone, to get to about 100 milliwatts. And this is something that my colleagues at Lund University and myself are looking into. I can't at this point go into too many details because we have a couple of patents pending, and there is also some exploitation plan, but we are shooting for that round number there. And I think we all agree that this is where we need to get to in order to make autonomous systems really viable. We can't have the control hardware, the control systems essentially being luggable if we want to build a small drone that flies around. That does not work, right? We need to have working autonomous systems that are able to do this, solve their tasks at a reasonable level of size and a reasonable level of functionality. All right, so let me go through a couple of other examples and some arguments for why we need HPC and high-performance computing technologies. I like to argue saying that we can't do all things in the cloud. We need to do a lot of things at the edge. So coming back to the self-driving car example, 6 gigabytes of data sent every 30 minutes is a huge challenge. Sorry, every 30 seconds is a huge challenge, even for the most advanced communication systems. Even for 5G, this is a challenge. So communication, overhead communication cost, even communication load on the system would be excessive unless we actually do autonomy at the edge, that is at the actual vehicles moving about. Another thing is privacy. So I think we all agree that we would not like to have our personal pictures, our personal information to be shared with everyone. But this is a clear and present danger if we do processing in the cloud. I think we all would be a lot more comfortable with systems processing locally and thus sharing the very basic detail, the very basic information needed in order to solve the tasks, right? Essentially, where am I, rather than how does my surrounding look like. Another thing is latency. Self-driving cars is one example, the drone is another example. We can't really depend on a cloud to react, or even perhaps not being able to react if you're flying about and perhaps crashing into something. So communication, privacy, and latency demands require us to do computation very, very close to the sensors, and in this case, at the autonomous vehicle. So if you look at what's happening here and looking at what we need to do, the tasks at hand, the data involved, the computation involved, and so forth, we see that HPC workloads and edge compute for autonomous systems, they are quite similar compute density. So we need to think of the embedded systems as sort of small flying or moving high-performance systems, because really it's that density of compute we're looking at. The good thing is that we can leverage HPC technologies here, and we do that a lot. One example is the drone I showed you. I'd like to go further and point to some additional examples. I think it's difficult to ignore in the last couple of years how important machine learning and AI have become. So for example, OpenAI has noted and has a very, very nice survey showing that AI training runs double in compute requirements every 3.4 months. This is a quite aggressive exponential growth. And in fact, it's projected that we will see more than 20% of all energy production in the world going into compute, a large portion of that going into AI. And I'd like here to bring up a couple of things. When this discussion is brought up, I hear a lot of comments about, well, okay, this is about getting more GPUs or getting more hardware or whatnot. I would argue here and give some examples that this is not really true. Hardware and GPUs are not quite often not the bottleneck. And in fact, we need to leverage HPC technologies. So this is an example from industry. And a company where I had the pleasure to work at for a period of my life, where I got the information that, well, we have some nice GPUs, but we only running them at 13%. We can't get them higher, so they're useless. We can't use them for everything, right? I mean, why are we even bothered with GPUs? And I felt, okay, no, this is not quite right. So I convinced I convinced my colleagues that I was allowed to look into this and also work with a couple of good friends and colleagues of this. So we did some analysis of this. So the first thing we did, we looked into the system and figured out that, well, you know, one bottleneck, the first bottleneck we saw was not GPUs, but actually file system bottleneck. We had the file system performance was not good enough. This was a state-of-the-art data center file systems, but it was several orders of magnitude slower than the GPUs. So we implemented a quick and dirty but HPC level storage stack instead, and we got the performance of the GPUs radically up, however not at 100%. So we in fact to the draw board, look into the system again, and saw that, well, okay, the GPUs are always waiting for data for the CPUs. And it was that the system was not balanced well enough. We didn't have enough CPUs with respect to GPUs. So we rebalanced systems, having more CPUs working on the system in tandem with GPUs, and we got 100% GPU utilization. This is a quick example of how leveraging HPC technologies and experiences in the AI domain can give you a substantial improvement of performance. So we got here 8x by essentially throwing no money at the problem, but rather tuning the system, leveraging experience well known from the HPC crowd. And this has been seen by several people also since a couple of months ago. I also worked with Tobias Jensen at Aalborg University, where they had a similar experience, and we saw that it was consistent with my experience from that company. And we also see a lot of players invested in HPC hardware to solve AI problem. One example is here to the right-hand corner from an installation where you essentially use HPC systems to solve AI tasks at great efficiency. So another example we see is with digital twins. Again, the prior talk talked about this as well. This is an example of a self-driving car. I was not involved in this. This is actually stock footage from Wikipedia under Creative Commons license, so it's free to be used. But I worked with systems looking very much the same. So you fill a car up with sensors, here sensors on the roof, but also compute everywhere. And then you drive around that car, having the compute part of the car checking what the driver is doing and learning from the driver and running several different algorithms in parallel in order to figure out how to drive the car. This requires you to address the problem of autonomy from HPC perspective in order to be able to actually have the compute power required in the car and having it running on the road without having the car turning into a truck. So these are just some examples. I can see that the clock is ticking, and that's actually quite good because I'm getting to the summary slide. So again, I would like to argue vigorously that all autonomous systems need HPC, that HPC is a fundamental enabler in many domains, including autonomy. And HPC technologies, as I've shown, can be used across the technology stacks in many different application domains. And actually by doing so, you can enable new possibilities in system design and allow for new and innovative systems to be developed. And now, given that I'm here and have the stream, I thought also I would provide you with some important information saying that DTU is taking a proactive stance on actually leveraging HPC and HPC in many different domains. So we have a new HPC laboratory that is gaining traction. It focuses on research on HPC technology. We are open to engage with everyone, including, and I hope that we will do that very fruitfully with the center. But we are also open to working with any of you of solving your problems. And we are also open and working across different universities. We have several persons working with us across Denmark. And we truly believe in open, inclusive, and transparent processes. We believe that this is a very exciting area to work in, and many can benefit from our expertise and technologies, but also to work with us. So I hope you all are interested in hearing more about this. I'm not going to steal the thunder in any way, because of course we're celebrating the opening of a new center here, not about me talking about weird and nerdy things called HPC. But if you do interested in talking more about this with me, you have my contact information there. And I believe there is time for questions. In the meantime, you can enjoy looking at the drone flying again. Thank you so much.
So I will thank you very much, Sven, for the very interesting presentation. I will bring you back, if you can. Yeah, well, we can see you, so no worries. There is room for question, please. Lazarus. Yeah.
Because I'm sure it's working. Thank you, Sven, for a great talk. Very inspiring. I would like to have your opinion. So apparently there was a period some years ago where the clusters were the way to perform serious computing, and then it sounded outdated some years later, and everybody had the computing capacity at home. And now deep learning came, and we're all looking into high-performance clusters once again. But then people are also a little bit objecting. You also mentioned doing computation on the edge. Why should I share my data with DTU or whoever owns this cluster? So right now, I think the state of the art, at least where I work in, which is robotics, is that edge computing is good for inference, but all the training takes place somewhere else. So do you see this trend changing and doing also training on the edge, or is this something we should leave to the clusters?
Thank you. This is a very, very good question. And I fully share your viewpoint here that we see a shift of computing power going back and forth between different entities. So I think for the foreseeable future, and the foreseeable future here probably is a couple of months, unfortunately. Things are happening very fast in the AI machine learning domain. I think we see training activities going on in clusters, at least in large-scale installations. I also hear and see a lot of innovation happening in training algorithms, and I'd like to point to last year's Turing Award awardees, who we all know was the founder of the modern machine learning AI revolution. They pointed very clearly to that we need to see more training algorithms that actually can scale all the way to the edge. And I think this will happen. I'm not sure when. I've seen some people looking into this direction. I'm not sure I'm all that convinced that they're having the right approach, but it will happen. In the meantime, we need to do this on clusters, I believe. The other thing I would like to point to is that we should not see this as completely separate systems. So I'm a firm believer in something I tend to call, and many with me call, the computing continuum, where we're looking at where does it make sense to place compute. So there are certain elements of a system that make sense to put on the edge. There are certain elements that make sense to be put in the cloud or in intermediary nodes between the edge and the cloud. And then we have elements that are in need of the highly specialized, compute-intensely aspects of high-performance computing. But that said, I think the main getaway here is that HPC technologies can benefit all of these technologies, including the cloud computing. So even though HPC in the past probably have seen as a very specialized technology, we see now that exactly the same technologies are applied in the cloud for AI training, but also at the edge in order to handle the sensor input, doing SLAM, doing sensor fusion, and so forth. Thank you for your question. Sorry for a very long answer, but it was a good question that deserved a in-depth answer. Thank you.
Okay, let's thank Sven once more. Thank you very much. And I would like also to say that, of course, I look much forward to know more about the new laboratory. So at some point we shall schedule a meeting so that you can make me more knowledgeable about this new initiative.
I will be happy to bring some cake.
Thanks. So now let's introduce our next speaker. While the PowerPoint fires up, I would like to welcome to the stage Tommy Erdbølle-Madsen, CTO from AgroIntelli, which will give us the perspective of AgroIntelli into agricultural field robots.
Yes, thank you for the invitation. I'm happy to be here and also to see that agriculture takes a certain part of the presentations today. So I will come from a little bit other perspective than Morten, because I'm coming from a startup, so we are kind of just jumping in on robotics. But in my talk I will show a bit about what AgroIntelli is doing, and then a bit about robotics in agriculture in general. And then some of the work that we're doing together with DTU. So first here a video of our robot seeding a field, fairly big farm in Czech Republic. So this is a typical operation for our robot. So it will seed, so we know very precisely where it's seeded, and then it will be able to cultivate between and mechanically remove the weeds between. Good. And as part of this, we also just had new investors, so we are fueled for the next years ahead. So this is our robot. It's designed for high precision agricultural tasks. It interfaces standard implements. So of course they have to be somehow simple or ready for this level of automation, and that you can detect errors on the implements and so on. Our robot comes in two different variants, so 150 horsepower and 75 horsepower. The navigation is based on GPS, high precision RTK GPS. And our safety system is based on cameras, so running AI to detect people, LiDAR to detect the objects in 3D, and also a bumper, and then geofencing, as it's really, really important for a robot like this that is not getting outside of the field. That could be one of the worst things that could happen. Here below is our cloud planning tool. So a lot of this planning is going on in the cloud, where the routes are done and tasks are created and then synchronized to the robot that then goes and performs the task. So today I think it's good to mention about our history also. It's based on a lot of university research that's been going on since around 2000. And then all the way up till today. AgroIntelli was founded in 2015. And the first years was a lot about technology development and making the robot ready. And now it's more scaling up production. So I'll just show a few examples of this research. And this one is a bit funny for me because it's my master project from 20 years ago. So that's pretty done here at DTU. And the next one is also a collaboration with DTU and KU Live, where a tractor was rebuilt to go out and do autonomous tasks in the field. So there's been a lot of other research in Denmark with SDU, AU, Aarhus University, and so on. So there's been a lot of field robots developed, and this is what we are harvesting some of the experience from today. So a little bit about the motivation. Brought in two pictures here. One is in agriculture, there's a lot of manual labor. Of course, driving a tractor is not the worst thing you can do, but still for organic farming, and there's still, you have to go out, even for sugar beets today, you often have to go out and actually manually remove weeds. So that's one of the drivers, this manual work. Another one is related to, this is the development over 50 years from, this was what a combine looked like. This is a kit, so it's not too big, but today you talk about 15 meters of width of combines, and tractors are evenly big, well, not as big, but they're also very big. And this also creates some damage to soil and so on. It's also something that is addressed a lot by using tracks and different stuff, but it's really gotten really, really big, and this also has some disadvantages in terms of flexibility to deploy your vehicles and so on. And this is an example of what can happen if you drive too much with very heavy vehicles. Then your soil gets so compacted that the soil is not draining away the water as good as it should do. So this is also part of the motivation for small vehicles. Then I brought in a couple of slides with just robotics in agriculture in general. So if you are looking into this space, a lot is going on. So I would say I could show at least 30 companies that's been coming out for the last about 3 years. So on this slide I have some smaller ones, and on the next one some bigger ones. But as you can see, there's a lot of companies trying all different kind of concepts to see how to address the agricultural market, which is also a very diverse market with a lot of different requirements. A lot of niches, I would say. So this is some of the smallest one from French NIO, just going in between the rows. This one is also a fairly successful one, I think. All of these are still small numbers, but it's a logistic robot just doing the task, driving in between wine rows and picking. So you can load your box and it will then go out automatically. And it will do a follow me thing, so you can easily teach the path and so on. So it's like an MIA AGV kind of vehicle moved into agriculture. Another Danish company, solar-powered electric robot, seeding and weeding. And then if you go to the bigger ones, then you see more of the big players come in where they try to automate tractors. So for example, Kubota, in Japan, the age of the farmers are around 60, I think. So the government there has actually made legislation that fits autonomous farming. So I think in Japan, the big companies, they actually dare to put out robots because they have a legislation framework they can work with. Here you see another very specialized one, which is also commercial. It's a sprayer going into orchards, spraying, and very simple operation, very focused. So I think that's a good example of automation in agriculture also. This is then the big players, so CNH, autonomous tractor, John Deere, autonomous tractor, also electric, but they are all doing these big concepts work. I think ACCO is the only one doing a small, I guess some of the others are also doing smaller ones, but yeah. Then a bit to a couple of projects that we are doing together with DTU. So this is a project called Agro-Robotic Fleet, which is funded by Innovation Fund Denmark. This is together with DTU and AU, and it's about collaborative robots. So the DTU part is here about the communication. So today we rely on having a cellular connection. So we have 4G, now we have 5G, but it is for rural areas, it is a limitation to be dependent on that. Of course, the nice thing is it's really moving forward with getting good connectivity. But still we would like to get better communication between the systems. This is also with this eye here showing a bit of the transition that we're doing right now. So today you still have to have a supervisor in the field to have an eye on the robot. But this is of course a very limiting factor and something we really want to get rid of. So we're pushing very heavily on getting to remote supervision via the internet, so you can sit remotely, which also increases the requirements for safety on the robot. The next one here is a master project that we have, and it shows where if you have a self-driving car, the road is normally fairly flat, and but this is not the case in agriculture. In agriculture we have the crops, and the crops can hide the obstacles. So I think this is an ISO object defined in standards that you need to find, that need to detect, and it's described as it can be partly occluded, and of course you have to bring it into a relevant scenario. So if you take something here like this, then you get more occlusion, and something like this, you get even more occlusion. And this is of course a very challenging thing. So today we are more in this area with what we can detect safely. And then of course for us it's very interesting to push the limits on this and make it safe in even taller crops. So that's an important thing, and we have this project here going on where we're investigating the systems that we have, but trying to add a radar system to this and see what that brings of extra features. Yeah, so detecting these objects. And then that's my last slide, so I just want to congratulate with this new initiative. I think it's really great to see this. And we're looking forward to more cooperation with DTU on different topics. And then we have this robotic desktop thing here that I think will fit. So it's a kind of this size model of robotic that has been developed with some students, and Paul Popp here from DTU, he will get one here around Christmas time. So I hope that can drive around in the new room also. So. Good. That was my last.
Thank you very much. Then we will have to make sure that Paul plays with it after Christmas.
Yeah.
Thank you. There is time for questions. No? Okay, but then I have one. So you have shown us that the journey began quite some time ago, actually, with your master project in the early 2000, and now there is this finalized product, which of course you're bringing to market. You have not been a part, of course, of this journey from the beginning to the end, but could you tell us about some of the major obstacles and winnings that have allowed AgroIntelli actually to reach this innovation?
I think in the beginning it's a lot just about navigation and route planning, and there's been quite a lot of research on how to make routes in the field, so that's an important part of our cloud solution. Of course, basically in 2000 it was just about getting a robot with RTK GPS to actually drive a straight line and do a turn. But then the route planning part has been important. Then there's been quite a few projects. For example, the HACO was also a part of a project around safety. So all this where we've been in pretty close dialogue both with research but also some of the safety organizations has been an important part to really come to that step where we say, okay, we think it's good enough and safe enough to put on the market.
Yes. In this project you are pursuing now, you show that one challenge, of course, is about collaboration about multiple robots in the field, and therefore opens up the question about communication, transfer of information. And then the other one is that, although for a master project, I guess some initial steps towards the ability, of course, to be more knowledgeable about the environment. What do you see to be the next steps after this? What type of level of autonomy is AgroIntelli aim at achieving in the near future?
We're aiming at full autonomy, where at full autonomy you're still with a remote supervisor. So I guess it depends a little bit on these, with where you have the different levels, 1 to 5. You can interpret them a little bit different, but at least we want to get to the remote supervision. So maybe also combined a bit with teleoperation, but it's possible for the farmer or for a central place, for example, AgroIntelli, to have a service where you can actually supervise a robot. So these, I think these things are the most important ones. Of course, we depend a lot on the communication, so 4G, 5G, and so on.
And this will be my final question. It becomes, of course, very interesting when in such a type of product, of course, you enter in contact with the end user. And now, of course, you're saying, well, at least in the near future, we see some sort of remote assistance. Do you think that the farmers now, they are ready for this? I mean, they can clearly see the benefit of technology, and thereby they are so ready to upskill? Or, and if so, what are the challenges there? So, I mean, do you think that your company then will also provide training?
Yeah, so training is a very important part of it, and it's also something we've worked with over the last years to, as one thing to make people aware, farmers aware of this possibility, but also to train them is still something we're experimenting with, what is the best way to train. But it's actually fairly simple to get the robot started and running and so on. So it's more about seeing the opportunity, and of course right now it is first movers and innovators that are buying this kind of technology, and this farm, very big fields in Czech Republic, for example, is a good scenario for us where farmers are ready to buy something like this. So it depends also a little bit on the farm if it's actually suitable. If it's very small fields and a lot of road transport, it's not so good, but if it's big fields and connected fields, then it works better.
Okay, thank you very much. It's been a pleasure to be here. So our next speaker is Per Thompson, Chief Advisor at DTU Space, and as early announced from his colleague, Michael, Per will give us a tour about the TAPAS testbed for autonomous systems. We look forward to your talk, Per. Thank you.
Well, I'm here to, well, first of all, it's nice to see you all. I hope that you still are alive after this very intense and exciting day today. I've been learning a lot, at least. I've been hearing about all of these fancy and very nice developments that's going on in the fields of agriculture, of maritime environments, and car sensors, and computing, and so on and so forth. And today I was putting together this talk about the test bed in Aarhus for positioning and autonomous systems. And the ambition here is really to provide you a scenario or a reference scenario in which you can test these autonomous systems that we've been hearing about all day. So I will show you what it is, and I will talk about the design we've done and give you a few project examples on what we're doing. The project here is done together with the Agency of Data Supply and Efficiency, and it was opened back in 2018. And the ambition has been sort of to make this reference scenario for testing, development, and verification of autonomous cars, robots, and sensors. So we were hearing earlier today about all the radars, LiDAR radars, sensors, cameras, and so on. But in order to certify or to verify that they are living up to the performance that they're given, we need some external validation of these sensors and autonomous items. And this is where TAPAS is supposed to sort of give you this reference scenario where you can test your items in a real urban environment. And actually, this is one of the only test beds in a real urban environment, and that's what makes it kind of unique compared to many other test environments that you find in around the world. This goes for the autonomous cars, and it goes for the blue economy we heard about earlier. I remember that that one of the comments was that they needed, or you needed, environments in which you could test these autonomous maritime ships and sensors and vehicles. And this is exactly what TAPAS is all about. It's about having this verification platform. I'll get back to how we've done it, and it's the same thing with the drones. We are capable, or you are capable of coming with your drones and testing them in this real environment. And of course, in order to test your devices, the real reference you need is in many cases, apart from all the obstacles you see, but it's a reference to the real positioning, or to the actual positioning that you need to reference to. Apart from having all the autonomous vehicles, it was also the ambition to have a platform where you could validate external services. For instance, now 5G is coming along, and we have here an excellent scenario to verify the precision of 5G positioning, and also the new Galileo high accuracy services, which is coming in. They promise to give us 20 centimeters in accuracy in all three axes, but actually they do need external validation in order to be capable of claiming that, and that's also where TAPAS comes in. So, well, yeah, okay. Also things in the area of smart cities, ride sharing, smart parking, road pricing, types of that nature, types of developments in that area also needs to have verification of their positioning capabilities in order to get them legalized, in order to validate them, and that probably done or needs to be done during the development cycle as well. Initially, you start doing it in closed courses or closed test areas, and then as they mature, you need to go into the real environment, so to say. Now, TAPAS is kind of basing the technology on ordinary RTK networks, but the main difference from the ordinary RTK networks is that the ordinary ones, they are most of the systems in Europe, they have around 70 kilometers between the base stations. Many of them are based on GPS alone, and it gives non-real-time precision positioning, well, it's not really suitable for autonomous vehicles. You need to set up your local RTK network, or you need to have this reference scenario that we're setting up here with TAPAS. So that's what we've done. We've set up this scenario with 11 reference stations in Aarhus. You see here a map of the center of Aarhus and the harbor area and the bay area of Aarhus. And then, of course, this network, very dense network, where the stations are situated with 5 to 10 kilometers in between them, giving or enabling this the very high accuracy or very high reference scenario you need in order to test the autonomous vehicles. Now, in open areas, we verified that we can obtain accuracies of down to 1 centimeter in all 3 axes. And as soon as you get into the very urban environment inside the city of Aarhus, the references deteriorate a little bit due to the multipath between buildings. But as soon as are we talking about agricultural machinery or ships, then we are in open areas, and you have this reference scenario to which you can test your autonomous items in these areas. And this is just to show you, for those of you who do not know Aarhus, it's the second largest city in Denmark, and it's quite a dense urban area around the harbor area and the center of the city. The nice thing about this testbed is also that we are in close collaboration with the municipality of Aarhus. And they are very much aware of TAPAS and are using it in many of their development projects. So getting permissions to run some of these tests is also something which is in their interest. As we have heard earlier today, the legalization of all of this is really a challenge, and this testbed is supposed to be sort of also a certification area for some of these new developments that are coming in the near future. I mentioned that it was based on RTK. We have these 11 reference stations, and we have the users are with their rovers or the autonomous vehicles are playing around in the area, getting corrections from the central processing facility at DTU via a software system called GN Smart, a development done in Germany, taking in the latest technology with respect to PPP and RTK. Now, we are taking in all the various constellations, meaning both Galileo as well as GPS, as GLONASS, as Beidou, and this of course gives you more satellites on the sky, enabling better coverage and less multipath and higher reliability. Because reliability is also one of the key issues with TAPAS. It's supposed to give you this reference scenario in as many cases as possible with the current technology. It's made flexible. If you compare it to other RTK, I mean, there are quite a few other RTK services laid out in Denmark, and Tapas is not supposed to be considered as an RTK service. That's really important to state and to say. It is a test bed because we are capable of playing around with it, so that the users of Tapas can sort of inject what they need into their test scenario. So if you need this RTK network for one day to test various systems, we can take it out of the normal service and inject spoofing and jamming and multi-part issues into the system, so that you can see how the autonomous vehicles react to these kind of impulses or drawbacks, if you wish, in the system. So it's kind of you can also take out the reference stations and in order to verify what it takes, how much or how little it takes to maintain the positioning of the sensors and the systems that you have that you're playing around with. So it is a research and development platform, and it's a place we've developed it's a playground, so to say, and it's a verification platform a validation platform for external validation of autonomous systems and sensors in all domains, meaning smart cities, services, autonomous cars and robots, and on sea in the maritime development, as well as in agricultural developments. There is a limitation to the agricultural stuff because Tapas has a limited, or currently a limited area around Aarhus. But there are still some capabilities that we can use in order to test or use Tapas as reference testing for agricultural machinery as well. So it's aiming to be sort of state-of-the-art test platform for all these new autonomous vehicles coming in, and be a certification platform, if you wish, so that we can get these systems legalized and get them running in an urban environment amongst other people and other cars and other traffic in all aspects. And of course, it's a challenge, but in order to get there, we need systems like Tapas as a backbone. So there are many possibilities that you can make use of when you want to develop your stuff. Here's a few examples. The City Shark project, which is collecting garbage. There's a drone flying around the harbor area and detecting oil spill. If there is an oil spill, the City Shark drops collecting garbage, and then go and take up the oil spill. There is Gaptic, a buoy reference. There is Complex, a lawn mowing machine for parks, and there is Cabra Robotics, which you heard about earlier today from Mads Bent. And there are a few other projects as well. So it's just to give you a little bit of a feel for what you can use it for. It is available, and it's working, and it's been tested and verified, and please join us if you wish, and also congratulations to CCAS in the future, and I hope that all these developments that you are doing in the coming future will come to Aarhus and test all your fantastic projects in an urban environment. So with these words, I will ask if there's any questions.
Well, we certainly look forward to come to Aarhus and test such a great infrastructure. I would like to open the floor for questions. Please, Jacob.
Yeah, from Lloyd Trista. Per, in terms of the antennas that you put up, if you want to extend the network, for instance more westward to the other parts of Aarhus, in terms of, for instance, collaborating more for incremental data, how many antennas is required to extend an area, so to speak?
Well, you saw these triangles, or this network that I showed on the map, and as soon as you can make a triangle with about 5 to 7 kilometers between the points, then you have this sort of a stable network you can rely on, and then you can extend it to whatever you want, actually. Having in mind that this is not an operational service but a testbed. So it's important to say, because we've had a number of complaints, people who are very anxious about us getting into their business, their businesses, and that's not the objective of all of this. So you can extend it, but having in mind that it's a testbed. And that it is meant for development and research. It's not an operational site. So yes, it is possible to extend it with an antenna or two, and then thereby extending the area that you need to, or that you would like to have as a research platform. But yeah, I hope that answers your question.
I have a question for you, because of course, this type of infrastructure sits within the city of Aarhus, and
sits within
the city of Aarhus, right?
Yeah.
So, of course, it presumes that the administration or the local governance has been a part of the journey.
Yeah, and they are.
How have you experienced this collaboration with the local authorities in setting up an infrastructure that, of course, is very much needed, and thankfully it is here today, but of course there are also, so to say, once again, safety and security challenges, so to say, different type of vehicles, flying, sailing, driving around. How the city hall, so to say, of Aarhus has approached the problem, if you know.
They have been incredibly open-minded. The digitization, chief of digitization, Søren Dahl in Aarhus, and all his colleagues are extremely open-minded and have been very much involved in not only the developments. The mayor of Aarhus has also been very curious to see what we can do here. So I mean, until now, they have been very open-minded, and also have initiated projects and seminars, and in order to sort of make use of this platform themselves. So they are also the sites that we've selected are done in collaboration with Aarhus, and we have this collaboration agreement with the municipality of Aarhus, or between the municipality of Aarhus and the Agency for Data Supply and Efficiency, I can't really find any negative things about about this. Of course, if you want to run an autonomous car in the center of Aarhus, I'm pretty sure that they will have to bend some arms in order to still close some roads and so on for some time, but that's for security reasons, right? But they have been very, very open-minded, to say the least.
Yes, that's great to hear that also here in Denmark we have forward-looking, so to say, administrations that, of course, will allow us to test this type of technologies in the real environment.
I think it is actually Trafikstyrelsen who is sort of most conservative in all this, but that's another story.
Yeah. Okay, let's thank the pair once again. And I'm now welcoming the last speaker of the day. I'm glad to welcome to the stage my colleague Silvia Tolu, assistant professor at DTU Electrical Engineering, that will close this day with a forward-looking talk about embodied intelligence and giving us a sense of what the future could look like in robotics and autonomous systems.
Thanks, Roberto, for the presentation and invitation, and also thanks to the organizers of this exciting event. Of course, I'm advantaged. I work here at DTU as assistant professor, and today I'm here to present you about my last research findings about how to enable intelligence in artificial systems. First of all, the general research area of this work is neurorobotics. Neurorobotics is the combination, the combined study of neuroscience, artificial intelligence, and robotics. What we do in neurorobotics is to study the brain in real agents, such as the mouse, as you see in this picture, and to study the interaction of the brain with the environment and with the body of the agent. And once we have a brain model, so we can simulate it, and together with systems, artificial systems such as robots, can be simulated, or real robots. But of course, when we have realistic brains that comprise millions of neurons, such as our human brain, what we have to do is to adopt realistic realistic body models, and also because what we want is to accurately represent data from neuroscience as much as possible. And we need also realistic environments, because then we want to see developing and growing skills of those agents, and once we achieve that, then we can reverse engineer the brain. Here is an example of a work we have done. It's about adaptive locomotion for hind limb locomotion of a mouse. You can see here the mouse, musculoskeletal, a musculoskeletal model of a mouse that was working before, and now it's not working. Yes, now. And yeah, I know it's a bit weird because the mouse is working on the hind limb, but we did it because we wanted to reproduce exactly the same behavior that we can see in human beings and also real mice. Actually, this is an experiment that neuroscientists do. We have a split belt, and suddenly one velocity of one belt is modified, and then we want to study the brain, how it comes, the adaptation of the body through the locomotion task. And we made a hypothesis based on the neuroscientific findings that the cerebellum, one part of our brain, could make a spatial adaptation by modifying the step time of the gait parameters. And what we noticed in our experiment here was that actually the cerebellum was modifying the pattern formation of the spinal central pattern generator in order to, by modifying the parameters of the interlimb and not intralimb. And this agrees completely with what we see in experiments with human beings. Now, my own research goal stems from, in neurorobotics, stems from the motivation of having agents that can autonomously operate in unknown and changing situations. That's why at DTU we have been developing bio-inspired control architectures, and I truly believe that by doing this we will open revolutionary robotic paradigms, because those agents will be able to really learn from real-time performances or movements, and we will be able to, in this way, to understand the relationship between the brain and the body body, and by having very less amount of priori knowledge. So if we achieve that, so we can open as applications, for example, safe human-robot interactions, and we will have robots operating with other robots or human beings, such as in manufacturing or assistive living applications, or even we will have the robots serving us as a tool for the diagnosis or rehabilitations of brain disease. Basically, this is what I'm investigating, my research goals. If you are not yet convinced that we need a brain for obtaining autonomous systems, think about the three main key principles for achieving that. One is learning. I hope you agree with me, is the master key, and it's a system property, so it requires plasticity. The second one is embodiment. We have the perfect body and the perfect brain to do something. Think about, I have here a pencil and my hand, and the hand is the perfect tool I have for doing things with this pencil. I don't need to know exactly the shape or the consistency of this pencil, because I've already learned it thanks to my brain. In robotics, what we do is measuring the size, making other kind of computation in order not to break it and to accurately manipulate it. So again, finally, we have autonomy, and this requires a brain, because I have to interact with objects, external worlds, my body itself, and so on. Let me give you a couple of lines about one of the most complex parts we have in the brain, which is the cerebellum. Actually, it contains 80% of the total number of brains in the world brain. At DTU, we have been studying that. We have now a very plausible model of the cerebellum, computational model, and it does many things. But what I want to remark here is that the cerebellum is a sensory area, so it receives information from everywhere, from our body and from the external world, and it provides corrections, motor and non-motor corrections. And what is very remarkable is that it is a data-driven area or structure, which means that we don't need a program. We don't have a program. We are born without a program. And why? Because our body is changing all the time since we are born until the end. And we don't know how it will change this body. The cerebellum just learn on the way. And how? By creating maps. So the brain takes all the sensory information and constructs maps, and those maps are used to accurately perform the movements and precisely perform the movements. Those maps are called internal models, and there are different types of it. I'm not spending time in explaining details, but in robotics we have used such models in order to have these performances. So more precise coordinated movements to mimic behavior of natural process and to achieve more systems control compliance. Because as the brain does, it predicts the desired outcome by providing very small forces. And at the same time, it's very precise. What I'm going to do is give you some examples about these two first and then these last. Before that, I would like to tell you that the results were obtained in the framework of two European projects. The first was my Marie Curie project by Biomodular, and the second is a flagship funded, actually the most ever funded flagship by the European Commission to reveal the mystery and complexity, the mystery of the complexity of the brain. What we wanted here at DTU was not to achieve very high performances directly through robots, but to achieve robots that can learn by repetitions by using supervised learning in order to have them flexible and that can learn different things in different situations. So these are two examples that used both of them cerebellar internal models, and the first one was made with the humanoid robot ICAP for online sensory motor adaptation, and the second one was made with in simulation also with a modular robot called Fable by Shape Robotics in a 4 legs configuration, because the first one was for manipulation and the second one was for locomotion. In both works, we used also machine learning techniques and evolutionary processes in order to facilitate the learning and obtaining a very online representation of the input space. In these are the three examples. We used the Fable robot, in which we embodied a spiking neural network, spiking cerebellar model, and we did it on the neurorobotics platform that was built within the Human Brain Project, and we used also a neuromorphic chip to allow fast computation with the real robot, besides the computational effort of the neural network. Now I want to give you an example of how to mimic a behavior. In this case, the behavior is the gaze stabilization. As human beings and other animals do, we are able to stabilize our gaze by using the internal models of the cerebellum. And we refer to our vestibular system. In the vestibular system is used together with 3 reflexes, which are the VCR, the VOR, and the OKR. The first for head stabilization, the second for minimizing the retinal image and the motion, and the last one for stabilizing the eye movement with the scene I'm observing. In this work, it was the first time we were able to couple the 3 systems all together, and we obtained exactly the same behaviors we have in human beings with the humanoid robot ICAB in simulation. Now look at this video. Here you can see a guy performing crazy stuff. Maybe you can think, oh, he has been training quite hard for a couple of years maybe, or months, who knows. What I can tell you is that he has done it since he was born. And this is what we do, all of us, by a process that we call motor bubbling. Motor bubbling is the generation of random movements, and we do that to explore our space and creating sensory motor maps. So, in this work, what we did was to take advantage of this behavior of the motor bubbling, and we developed a spiking neural network for unsupervised learning that took the data, gathered the data from the sensors, also both proprioceptive sensors and exteroceptive sensors, to perform this motor bubbling. And we demonstrated, by building this control system, that the spiking neural network was able to handle with the noisy readings from the sensors and to achieve an accurate performance during a simple visual servoing task, as you can see here with the universal robot arm. Yes. Then we did it also with 4 degrees of freedom. In this other work, we combined unsupervised learning with supervised learning. So we took the same coarse controller we had previously for performing motor bubbling, and on top of that, we put the cerebellar models, cerebellar controllers, in order to increase the performance during the servoing task. What we demonstrated was that the cerebellum was able to reduce the error during the reaching task and increasing the number of successful trials, as our cerebellum does. Okay, there is a lot to do, and here I put just some answers, like pieces of a puzzle, for achieving all these things, such as learning with fewer labeled samples. I know there are already techniques for doing that, not very implemented in robotics. What we want to achieve is versatility, flexibility. That it's still a gap, especially with also with the deep neural networks that we all know. It's very complicated to achieve that. But I mean, these are answers possible. We will try in the next future. What in the meanwhile I can anticipate we are doing for the near future is implementing our brain controllers into soft robots that represent more challenges, you know, especially for dynamic control. And in this way, we aim to reveal more the evolution of the brain-body relationship and make a breakthrough in model-free learning. And we have also been investigating tactile sensing for robotics grippers. I hope you saw the demo in ASTA before. And together with Graspian, the company, we have integrated their resistive sensor into processing communication interface and a control loop. So, in the long-term future, we have been building an interdisciplinary team to integrate neuroscience, experimental neuroscience with device fabrication and cognitive brain-based architecture that will open a new domain in underwater robotics. And if we understand the brain, then we can understand when the brain doesn't work. So we can reproduce pathologies of the brain, and we then use the robots as a tool for rehabilitating those pathologies, such as Parkinson's disease, which I'm currently investigating now, together with the Paragit company. And that's it. Thank you to all my collaborators and to you. Any question?
Thank you very much, Silvia. Please, Lazarus.
Silvia, usually they say like ladies first, but now I understand why lady was last. So thank you for a nice and inspiring and forward-looking talk.
Thank you.
My question would be maybe a little bit philosophical. So there is this Socratic notion, like, I mean, I can think about something and then solve it. And then you gave us some examples of modern publics of how we actually take action very seriously in order to be able to just fit something in our mind. You also saw that learning is an important thing, but the embodiment is also important. So usually what we are doing nowadays in robotics is that we do some machine learning model without taking into consideration how a robot looks like. We just make a generic model and then we just plug it to this robot if I happen to have this one, or that robot if you happen to have that other one. So how would you see like this coupling of what is my target hardware with what should be my learning mechanism? If there is an answer, maybe there's not that. I would like to have your opinion on the thing.
Thank you. For sure, it's a complicated question. And yeah, what you have been doing is the opposite method I do. So you start looking at the robot, and then you try to fit an algorithm to that. What I've been explaining is, no, we look at the algorithm, and we take a imitation. We want to imitate something that already exists, that we know that works very well, for sure, and then fit it into a robot. So far, we have seen that the neural networks we have fits any kind of robot, okay? Because what we do is try to manipulate the neural networks for achieving the behavior. But then, when we use it, we see that there is an evolution in the learning, in the plasticity or synaptic plasticity of the neural network. So we see that there are things different in each body. And this helps us to not only understand more, but then to even fit the neural network even more, to that body, and obtain superior performances. So it's not the same if I do this or if I ask my cat to do it. Okay, he has a different, of course my cat is not able to do this. Bad example, but you understand me, no, right? So we have different brain, but of course my cat can do other things that I cannot do, because he has a different hand. Okay, so let's start by understanding like the framework of the brain, and adjust it to it. I think it's easier than going to the other way around. If I replied.
Okay, thank you very much for your vision about the future of robotics by combination of AI and neuroscience. It will be interesting to see how soon this will happen. So we are at the final bits of the day, and I will try to be short, since you have already been patient enough with us. But I think some concluding remarks are due from my side, since today I had the easy job. I let my colleagues to do the hard work. So I think that you will also like to hear a bit from me. And indeed, it's been a long and an intense day, a rich program with knowledge and experiences. And I certainly hope that despite the different areas where you come from and the multitude of point of views that we have offered you, each of you will go home with a value gained and seeing an opportunity for future collaboration. If there is a message that clearly stands out from these long or this numerous amount of presentations, is that by establishing the Center for Collaborative Autonomous Systems, DTU wants to strengthen its existing leadership on autonomous systems and become an international powerhouse. The launch of the center today should not be seen as the beginning of something new. DTU is not venturing all of a sudden into the unknown because that's the trend. But the natural continuation of 2 decades, if not even more, of outstanding research, development, and innovation on autonomous systems, and we want to do this in a bigger house and a stronger one. In the recent past, we have all witnessed how roboting messages and headlines a few years back have not been followed up by the delivery of the promised land. Today, in several instances, we've been discussing about the self-driving car and how we're still waiting for it. I don't know how many of you have placed the autonomous car in the shopping list for 2020, but as we all know, it will not be under the Christmas tree this year. Maybe in few years from now. As a scientist, I do not see this as a failure, but only the evidence that the amount of research needed in order to get to that level of autonomy, to that dream come through, is still large, and research and development is needed in order to witness fully autonomous systems, especially if we envisage them to be an integrated element of our society, where some of them, not all of them, will have to work shoulder to shoulders or coexist with us humans. Much of the needed research, as we discussed today, is technology related, but is not technology focused. Some of you may have heard about the recently released Molly problem, which I would like you to make familiar with. A young girl called Molly crosses the street without anybody attending her. And on the way to the other side, it is hit by an unmanned self-driving car. There are no eyewitnesses. The question is, what should happen next? The Molly problem clearly is not unique of the automotive industry. As we know, for example, from our research on the autonomous ship, the acceptable level of failure of systems of this type is minimal. We cannot go by the standards of other type of communities where 5% or 10% of classification or misclassification is acceptable. Here it is not. These problems are formulated and debated to understand the public expectations in the autonomous system behavior during critical situations. Therefore, in order to actualize, or the actualization of autonomous systems in different areas of society strongly depend on the ability to certainly innovate technologically, as well as the ability to generate public acceptance and understanding the changes in workflows that the integration of such technologies will necessarily demand. We cannot expect that from one day to the other, people will accept naturally, as John told us, to see machines walking but just on the side of where we walk and doing the jobs that we used to do. To best address this twofold challenge, decoupling the governance of the technology from the technology development will result in limited acceptance and adoption and restrained technologies. We will simply, at some point, if we do not govern the process, we will have to renounce to some features. To best address this twofold challenge, DTU builds the Center for Collaborative Autonomous Systems by bringing together the hardcore technology developers from the electrical engineering, computer science, and space technology domains with our specialists in technology management. Now, allow me to give you a sense of perspective. It's natural, after such a long day, to go back having at least the answer to a basic question: where are we heading from now and from here? Well, thanks to the commitment of our funding departments, we will launch the first flagship project within the second quarter of next year. And this is why we will initiate an internal process where our scientists jointly will have to promote their research ideas within, of course, the area of autonomous systems. These ideas will be evaluated externally, and then there will be the first flagship project emerging from this process, which will be initiated, once again, thanks to the financial commitment of DTU Electrical Engineering, DTU Management, DTU Compute, and DTU Space. What else? The center has the ambition to develop and to operate on two timescales. As an institution, as an academic institution where we create knowledge, we need to have the ambition to look very far down the road. At the same time, if we want to collaborate with industries here in the country to strengthen their positioning nationally, internationally, we need also to be able to deliver on shorter time frames. And that's what we have the ambition to do. What we will do in the coming months, and of course throughout 2021, is that we will initiate a series of idea co-generation workshops, of course rooted here at ETU to stimulate dialogue and brainstorming among the scientists that have to actually build from the bottom up this new house in order to identify groundbreaking, high risk, high gain research ideas which bring autonomous systems into the sustainability agenda of the United Nations. Interested industrial stakeholders will be invited to contribute to such a workshop because we believe that the views from people outside DTU will be valuable in order to identify the best ideas, and also because when we do not commit to develop something for tomorrow or for today, industry may be more willing to open up and collaborate on a more relaxed basis. At the same, this process, of course, will generate long-term research paths to develop technology that we expect will revolutionize the area in 5 to 10 years. That's our long term. At the same time, we look forward to all the collaborations that we can build with our industrial stakeholders within the center to address outstanding issues that will get us closer to have some level of autonomy in the different domains in much shorter time frames of 2 to 4 years. And here, of course, we invite our industrial partners to come and solicit us to actually address problems that are outstanding. To conclude, the Center for Collaborative Autonomous Systems is a new collaboration arena to best address the multifaceted challenges that the actualization of autonomous systems present. Today we have seen that a lot, of course, has been done, but we also have got a clear idea that a lot remains to be done in order to see such a technology to be present in a more pervasive way in our society, and also to be fully accepted, first of all, by ourselves, that we need to live with that. The center, as I said, as such, is not entering in competition, certainly not with the departments that are helping to fund it. We're not in competition with industry or our other academic university realities here in the country. On the contrary, the center is born to collaborate with universities that share our vision, to collaborate with industrial stakeholders that see on autonomous systems the way to strengthen their leadership, and to collaborate with concerned public and private institutions that would like to understand the societal implications of having systems, autonomous systems, coexisting shoulder to shoulder with humans. Said that, I would like to conclude by giving a few thanks messages. I would like to thank my colleagues, Jan Madsen from DTU Compute, John Pauline Hansen from DTU Management, Matteo Fumagalli from DTU Electrical Engineering, and Michael Leonard-Werner from DTU Space for being with me to do the heavy lifting in the first months of this new and incredible adventure. I would like to thank the staff that has helped to put this together today. Without them, it will not certainly be impossible. I would like to thank all the speakers that have come here and made us all more knowledgeable about what has already happened at DTU and outside DTU, and what are the opportunities and challenges that we need to address in the future years. I would like to thank DTU, of course, for the opportunity that is giving us, and myself first. And last but not least, I would like to thank all of you present here and virtually to be with us today, and I look forward to collaborate with each and every of you. Thank you.